Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 17 on the indefinite integral.
Welcome to Chapter 3 on integration. In this chapter, we're going to take what we've learned about differentiation and run it in reverse. In today's lesson, we'll begin with an introduction to the indefinite integral and see its applications and motivations in differential equations.
We begin with a definition. The indefinite integral of a function f of x is the antiderivative of f. That means if you take the integral of f and differentiate it, plug that into the differentiation operator, then what you get back is f. You may think that this means that the integral is really the inverse of the differentiation operator. Well, that's almost true, but not quite. If you reverse the order of operations and first compute the derivative of f, then what will you get when you integrate it? Will you get f back again? Well, not exactly. You may recall there is a constant of integration involved. And indeed, the indefinite integral of f is a class of functions, all equivalent up to a constant. It's fairly easy to write down a list of integrals that we can compute easily. The integral of x to the k we know is x to the k plus 1 over k plus 1, unless k equals -1, in which case you get the log of x. Integrals of sines and cosines are easy enough. Anti-differentiate and watch your minus signs. And, wonderful to tell, the integral of e to the x is, of course, e to the x. Don't forget the constants. That much is simple. Take the antiderivative. On the other hand, there are some functions for which computing an antiderivative is highly non-trivial. Maybe with work, you'll be able to compute an antiderivative for log of x or secant of x. But no matter how hard you try, you are going to have an extremely difficult time finding an antiderivative for something like e to the x squared. We're going to take some time a little bit later in this chapter to go over methods for computing these antiderivatives. For the moment, and for the next couple of lectures, we're going to spend some time answering the question of why. Why do we care about the indefinite integral? One excellent answer to that question is to be found in the subject of differential equations, where a differential equation is simply an algebraic equation on a function x and its derivatives. For example, the simplest differential equation is of the form dx dt equals f of t for some f. This equation has as its solution x, given by the indefinite integral of f with respect to t. Now, what does that mean? How do we interpret it? Well, one natural interpretation for the derivative is as the slope. So the differential equation is telling you something about the slope of the solution curve. It has to match this function, f. Now, of course, we can see the indefinite integral in here. We can see why there is a constant of integration. Because if I translate this solution curve up or down, I am not changing any of the slopes, and it still must be a solution. Thus, solutions to this simple differential equation come in the form of a family depending upon a constant. These are often called ODEs, which stand for ordinary differential equations. You will see some extraordinary differential equations later in your calculus career. For the moment, let's stick to a basic example and look at gravitation. As you know from your background in physics, when you drop an object, then it is acted on by gravity, which, near the surface of the Earth, is modeled as a constant, g. Now, we can model the behavior of this falling object in terms of its height, x, its velocity, v, and its acceleration, a. All of these are functions of time. Since acceleration is a constant, we can write the simple differential equation dv dt, that is acceleration, equals minus g. Note we put the minus sign in because we orient things so that up is positive, down is negative. Likewise, because we know the relationship between velocity and height, we can write a differential equation for x. dx dt equals v. Let's solve these one at a time. Both of these are simple differential equations. The first, dv dt equals minus g, has as its solution v, as a function of time, is the indefinite integral of negative g with respect to t. What does this have as its solution? Well, of course, the antiderivative of a constant is just that constant times t, and we have a plus c as our integration constant. What does that plus c really mean? It is really an initial velocity. Did we simply drop the object, or did we toss it at some speed? Well, in this case, if we plug in t equals 0, we see that v at time 0, otherwise known as v naught, is equal to this integration constant. Now, taking that solution for velocity and plugging that into the right-hand side of our second differential equation allows us to solve for the height, x, as the integral of v of t dt. We already know what v of t is, and so we compute the antiderivative to get negative 1/2 g t squared plus v naught t plus another constant of integration. What is that plus c? Well, that is really an initial height, since at time 0, all of the other terms vanish except for the plus c. So we can write that as negative 1/2 g t squared plus v naught t plus x naught. This should be a familiar formula to you from your basic physics. Whether it is or not, it is transparent now why projectiles move in a parabolic shape under the influence of gravity. We have a negative 1/2 g t squared coming from the integral. So far, so good. These simple differential equations have simple solutions in terms of integrals. But what happens when we look at the next simplest class, namely dx dt equals f of x instead of f of t? How do you solve that for x as a function of time? Well, we're going to restrict to the simplest, the canonical differential equation of this form, one that is linear in x. This is a very important differential equation. It is dx dt equals ax, for a constant. We're going to think about this one over and over. How do we go about solving this equation? Well, the first thing that we're going to do is look at it and think. dx dt equals a times x. Let's simplify and say that a is equal to 1. We're looking for a function whose derivative is itself. You and I both know an excellent solution. That is, x of t is e to the t. Now, what happens when we put the a back in there? Well, if we just think about it a little bit more, we see that putting an a up in the exponent gives us as its derivative e to the at times a. That is what we're looking for. We could, of course, put an arbitrary constant, c, out in front, and you may check that this is a solution to that differential equation. What is that constant? Well, we might, following our previous example, call it x naught, the initial condition, what you get at time 0. This method of solution is sometimes called solution by Ansatz, which is a fancy word for saying we took a guess and it turned out to be correct. There is, of course, a more principled approach. One such approach is based on series, where we assume that our function x has a series expansion, c0 plus c1t plus c2 t squared, etc. These constants, c sub k, are, to us, unknown. Now, what are we going to do with this? Well, the differential equation tells us something about the derivative of x with respect to t. We can differentiate the terms of this series very easily. What the differential equation tells us is that this is equal to a times x, which of course is a times c0 plus a times c1t plus a times c2t squared, etc. Now, here is the important step. If we have two series that are equal, then their coefficients in front of the various terms must also be equal. And now we can work one step at a time. The constant terms, equating them, tell us that c1 is equal to a times c0. Well, that's good. If we knew c0, we would know c1. What does the next equation, that of the first order coefficients, tell us? Well, it tells us that c2 is equal to 1/2 a times c1. But we already know what c1 is. c1 is a times c0. So that tells us that c2 is actually 1/2 a squared times c0. What happens when we take the coefficients of the quadratic term and set them equal to each other? Well, 3 times c3 equals a times c2. That means c3 is 1/3 a c2. Using what we know about c2, we get 1 over 3 factorial times a cubed c naught. I'm going to let you keep going with this and see if you can find a pattern. That pattern, through the method of induction, can show that c sub k is 1 over k times a times c sub k minus 1. And that is 1 over k factorial a to the k times c naught. That means when we look at our original series, x of t, it's the sum over k of ck t to the k, that is c0 times 1 over k factorial times a to the k times t to the k. Now, I'll let you verify that that is really c naught times the exponential function e to the at. We obtain our solution, which we already knew was true, but from a more principled series approach. That, however, is a little complicated, and so we are led to our last and best method of solution, that of integration. Beginning with x as a function of t, we differentiate using the chain rule to obtain dx is dx dt times dt. Now we know something about dx dt since this is a solution to the differential equation. It is a times x. And now we're going to use the method of separation, which means we move all of the x terms over to one side of the equation, and we keep the t terms over to the other side. This gives us dx over x equals a dt. And now, using the fact that the integral is an operator, we're going to apply it to both sides of this equation, obtaining the integral of dx over x equals the integral of a dt. What is the integral of dx over x? Well, it's the antiderivative, natural log of x. What is the integral of a constant times dt? It's simply at plus an integration constant. Now, to solve for x, we apply the exponentiation operator. E to the log of x is simply x. On the right-hand side, we get e to the at plus a constant. Splitting that up into a product, we obtain a new constant, we'll call that c as well, times e to the at. That is our solution, and it was obtained effortlessly. One of the things that you'll notice is that e keeps coming up. It is not a coincidence that e to the t appears as the solution to the simple ODE, dx dt equals x, or as the series, sum of t to the k over k factorial, or as the indefinite integral, as we just saw. In all three cases, you can interpret the constant of integration as an initial condition, or the constant term in a series, or the arbitrary constant of integration. And so the question of why the plus c has many answers.
And so we see that three of the main characters in our story cross paths: integration, series, and solutions to differential equations. In our next 3 lessons, we're going to focus on one of these characters, solutions to differential equations, and see how integration helps us to compute and understand them.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 18 on a simple ODE.
In this lesson, we're going to do one thing, and one thing only. We're going to look at a simple, single differential equation, consider some of its many applications.
This is the subject of today's lesson. dx dt equals a times x, where a is a constant. This is a linear, autonomous, ordinary differential equation. It is extremely important that you know this and its solution. X equals the initial condition, x naught, times e to the at. Now, what does this solution mean? What does it look like? Well, at time t equals 0, it passes through x naught, the initial condition. What it does from there depends on a. If a is positive, then you get what is called exponential growth. You get an exponential function in t that is growing as t increases. On the other hand, if a is negative, then you have exponential decay, where the values of x are getting closer and closer to 0 over time. Much of the importance of this equation comes from its ubiquity in modeling processes. You may have seen this equation used to model radioactive decay. If you look at, say, the radioactive isotope of carbon, carbon-14, then the amount I of that isotope changes to a degree that is proportional to I, where that constant of proportionality is negative. Likewise, if you look at the amount of a drug or medicine that is in a body, this changes over time according to the same differential equation, though perhaps with a different constant of decay. Both of these have negative coefficients and thus connote an exponential decay. There are some situations where you have exponential growth, however. If we look at the most simplistic model for population growth, one in which the size of a population, P, changes at a rate proportional to P. That constant of proportionality is a birth rate. This doesn't work so well for modeling human populations, but for certain settings, it's reasonable. On the other hand, continuously compounded interest is a fairly realistic model, at least in the short term. It says that the rate of change of the amount of money you have invested is proportional to how much is there. What is that constant of proportionality? Well, that is an investment rate. But what do we mean by continuous compounding? Let's assume an annual interest rate of R and an initial investment of money at time 0. If we were to compound our interest yearly, then after 1 year, the amount of money we would have would be our initial investment plus that initial investment times the annual interest rate. We could write that as the initial investment times quantity, 1 plus R. If, however, we compounded that interest monthly, then what would we get? After 1 year, we would have the initial investment times quantity 1 plus R over 12, which is how much we would earn in January. Then we would multiply all of that by quantity 1 plus R over 12. At the end of February, we would continue on until the end of the year, giving another factor of 1 plus R over 12. That means at the end of the year, we would have the initial investment times quantity 1 plus R over 12 to the 12th power. That's actually a little bit more than we would get from an annual compounding. Now, of course, monthly compounding is maybe not so accurate because they have different days per month. So we could do it daily and get the initial investment times quantity 1 plus R over 365 to the 365th power. I think you can see where this is going. If we take the limit, then after 1 year, we get the initial investment times the limit as n goes to infinity of quantity 1 plus R over n to the nth power. Now, I know you've seen that limit before. You may recall that it is, in fact, e to the r. This is a hint that the standard linear differential equation is really behind what's happening in continuous compounding. Let's see how that falls out. If we look at the amount of money at time t plus a small increment, 1 over n, then, according to our previous reasoning, this is the money at time t times quantity, 1 plus R over n. And what we want to do is compute a limit as n goes to infinity. Now let's change variables a little bit, and instead of looking at n going to infinity, let us replace 1 over n by h, where h is a small amount going to 0. Then the amount of money at time t plus h is, from the above, the amount of money at time t times quantity 1 plus R times h. And now, expanding out that multiplication, we see a familiar sight from our definition of a derivative. The coefficient in front of the h term tells us the derivative of the amount of money as a function of t, and so we can see the differential equation. d dt of the amount of money equals r times the amount of money. That is our standard differential equation. Now, there are many applications of this equation that go far beyond radioactivity and population and money. Let's look at an unusual one coming from linguistics. If we read English poetry from antiquity, we'll see some unfamiliar words. If you look at Chaucer, the Canterbury Tales, many of the words are unfamiliar to us. But if we move the clock ahead to Shakespeare's time, then some of that poetry is familiar, some is unfamiliar. Moving ahead a little bit further to Milton, things are still a little obtuse, but more, the words make sense, and we could keep going with Blake and others. What we might guess is the following linguistic model, namely that the number of words in English remaining in common use decreases at a rate proportional to the remaining words. That means that words fall out of use. But this model states that words fall out of use according to a linear differential equation, where W is the amount of words remaining in usage, and alpha is a decay constant. Assuming this model, let's answer the following question. If we find 20% of the words in Milton's poem to be unusual, then what fraction of Chaucer's poetry did Shakespeare's audience recognize? Ooh, that sounds difficult. What can we do with that? Well, let's say that t corresponds to the year. We're going to be interested in two functions of t. The first, w sub m, is the number of words in Milton's usage currently used at time t. That is, according to the solution to this differential equation, w sub m at 1667, the initial condition, times e to the minus alpha times the number of years that have elapsed since 1667. Likewise, we'll be interested in wc of t, the number of words from Chaucer's time still in common usage. This has the same solution with 1667 being replaced by 1400. Most importantly, the alphas are assumed same because this is all English. Now, what is it that we are given? We are told that the number of words from Milton's time in common use today, let's say in 2012, is 80% of those originally available. Plugging in the solution to the differential equation for w sub m when t equals 2012 and then dividing by the initial condition gives us a single equation that has only alpha as an unknown. We can therefore solve for alpha, and we get a quantity that is about 6.5 times 10 to the negative 4. Now, if we use that alpha in our solution for w sub c of t, then what can we get? Well, our goal is to find the fraction of words from Chaucer's time that people in Shakespeare's time would have understood. That is, wc of 1600 divided by wc of 1400. Plugging in our solution to the differential equation for w sub c gives us an answer of e to the negative 200 alpha. Since we know alpha, we can compute it. It's about 0.88, meaning that about 88% of Chaucer's words would have been recognizable to Shakespeare's audience. Well, that's pretty cool, but is that actually true? Well, I don't think so. This simple model that we've written down ignores so many features of linguistics, such as the creation of new words, such as the evolution of words. Words are constantly changing their meaning, so that even though a word does not fall out of common usage, it's really a different word with an altogether different meaning. Lastly, there is whole-scale evolution of language. I'm speaking American English, which is in some respects very different than British English. If you look at, say, computer languages, you can see, even over short timescales, very rapid evolution in the language itself. This brings us to an important conclusion that even though our mathematics was perfectly accurate, a perfectly accurate solution is only as good as the model on which it's based. If you have a bad model, it doesn't matter how good your math is, you can't conclude truth. So with that in mind, let's talk about zombies. and we'll model the zombie apocalypse as follows. The rate of change of the infected population is proportional to the uninfected population. If we denote by U of t, the uninfected population, and Z of t, the infected population, then P, the net population size, is a constant, that is U plus Z equals P. Our model says that dz dt, the rate of change of the infected population, is proportional to U, that is P minus Z. That constant of proportionality we'll call R. Now, what is happening to du dt? Let's think about that. U is P minus Z. So differentiating gives us du dt equals dp dt minus dz dt. Now, dp dt we know is 0 since p is constant. And we know dz dt equals r times u. And so we see that our zombie model is really just the linear differential equation in disguise for the uninfected population. We know the solution, u of t, is the initial condition, u naught, times e to the minus rt. That means that the solution for the zombie population, z of t, is p minus u of t, that is p minus u naught, e to the minus rt. Unfortunately, as t goes to infinity, this means that everyone is a zombie. Now, before you dismiss this differential equation as being ridiculous for modeling zombies, consider it may also be used to model the spread of disease, or the spread of propaganda, or the adoption of new technology in a population. This simplistic equation is not rich enough to really model these complex phenomena, but it's a good first approximation. It's even better when applied to heat. Newton's law of heat transfer is essentially the same equation. It says the rate of change of temperature with respect to time is proportional to the difference in temperature with the ambient environment. So in our zombie equation, this constant of proportionality, R, was an infection rate, and P was a constant population size. In Newton's law of heat transfer, the constant is a thermal conductivity. How easy is it for heat to spread? And the constant, A, is an ambient temperature. Same equation, very different interpretations. That's one of the beauties of differential equations.
And so we see one simple differential equation gives rise to so many applications. But what happens if we change that differential equation? How will we determine the solution? What is it going to be good for? In our next lesson, we'll consider some other classes of ordinary differential equations, their solutions, and their applications.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 19 on more ODEs.
In this lesson, we'll consider some new families of ordinary differential equations, their solutions, and what they're good for. Along the way, we'll learn some new methods and some new applications.
Among the many differential equations that you may encounter, a few families are worthy of note. Some ODEs are autonomous, meaning that the right-hand side depends on x alone and does not depend on t. Those equations that do depend on t are called non-autonomous equations. They can be very difficult to solve. Some, however, are solvable by the following separation method. If dx dt is of the form of a function of x alone times a function of t alone. Then, following the pattern of what we did for the linear differential equation, we can separate out all of the x terms on the left, all of the t terms on the right. Then it makes sense to integrate both sides if these integrals are computable, and if you can solve for x, then you're in good shape. Let's look at an example. If you consider a body that is falling under the action of gravity, you'll notice different behavior depending on its shape. This is due to drag force. If we assume a drag force model where that force is proportional to the velocity of the body, then what do we have? Well, our body is being acted on by a gravitational force of magnitude m, the mass, times g, the gravitation constant, pointed down. Pointed upwards is the drag force that is assumed proportional to the velocity v by some constant of proportionality, kappa, the drag coefficient. Newton's law says that the mass times the acceleration, dv dt, is equal to mg minus kappa times v. And here we have an autonomous and separable ordinary differential equation. By doing a little bit of factoring and algebra, we can move to the left-hand side the quantity v minus mg over kappa, all in the denominator. On the right-hand side, what is left over is negative kappa divided by m dt. Integrating both sides, what do we do? Well, on the left, you have to think a moment to see that the antiderivative of dv over v minus a constant is in fact the log of quantity v minus that constant. On the right-hand side, the integral is very easy. It is negative kappa over m times t. We'll put our constant of integration on the right side. Now, to solve for v, what do? We exponentiate both sides. On the left, we have v minus mg over kappa. On the right, we have e to the negative kappa over m times t. That's times e to the constant of integration. We're just going to call that a new constant with the same name, c. Now, solving for v, what do we have? v is constant e to the negative kappa over mt plus mg over kappa. Let's think about this for a moment. If we take a limit as t goes to infinity, what happens? Well, the exponent in the exponential is negative. That means that term goes to 0, and goes to 0 rapidly. What remains is a constant velocity equal to m times g over kappa. This is called the terminal velocity. Depending on the value of kappa, it may be very fast or rather slow. Separable ODEs also arise in analysis of a fluid leaking from a tank. This is regulated by Torricelli's law, which relates h, the height of the liquid, with a, the cross-sectional area at the top. The law states that the rate of change of h with respect to t is proportional to the square root of h and inversely proportional to a. If we consider, say, a cone or anything where the cross-sectional area is quadratic in h by some constant, maybe pi, maybe not, then we obtain h prime is proportional to h to the negative 3/2. This is separable, and moving the h to the 3/2 over to the left side, and then integrating both sides, yields, on the left, h to the 5/2 times 2/5, and on the right, a constant times t plus an integration constant. Solving for h gives a linear function of t raised to the 2/5 power, where the constants will depend on the physics in your initial condition. What this implies is that h approaches 0 very rapidly at the end. How rapidly? It is in big O of the final time minus t raised to the 2/5 power. That comes into zero very, very sharply when you're looking at something to a power of 2/5. Let's move on to a different class of non-autonomous ODEs. These are the linear non-autonomous ODEs. They're of the form dx dt equals a of t times x plus b of t, where a and b are functions of t. For example, dx dt equals tx plus 1/2 t squared is of this form. We say that it's a linear equation because if you suppress the t dependence, you get something of the form dx dt equals ax plus b. And that right-hand side should remind you of the equation of a line. Well, how do we solve such a problem? The method that we will introduce is that of the integrating factor. It's a little tricky, so hang on. Let us denote that integrating factor by I. We're going to multiply both sides of this equation by an as yet unknown function, I. Rearranging terms a little bit and multiplying through gives us I times dx dt minus ai times x. And on the right, I times b. Now, what is this good for? Well, if you look at that left-hand side and keep in mind the product rule, then you see something that should remind you a little bit of the product rule. If we had something that looked like I times dx dt plus di dt times x, well then, we would recognize that that's just the derivative of I times x. And that's something that's going to be helpful to us. So what would we need to be true in order to have this? We would need to have di dt equal to negative a times I. Now, focus on that, because what we're doing is deriving a differential equation for this unknown integrating factor, I. That is separable. That is solvable by the standard techniques that we've been using. When we solve that equation, what are we going to get? I is e to the integral of negative a dt, which we could write in shorthand as e to the negative integral a. If we choose such a function, I, and multiply both sides of our original equation by this, then what we obtain is on the left, the derivative of I times x. On the right, I times b. Now we can integrate both sides, because differentiation and integration undo each other. On the left, we have I times x. On the right, the integral of I times b. We can solve for x and obtain, after substituting in our formula for I, a scary looking but very useful equation. The solution is x is e to the integral of a times the integral of b times e to the negative integral of a. Let's demonstrate this formula in the context of a mixing problem. Assume you have a tank that holds 1,000 gallons and is 90% full. An additive is injected at a rate of 10 gallons per minute. The solution is mixed well and then drained out at a rate of 5 gallons per minute. The question is, what is the concentration of the additive at that moment when the tank is full? There are a couple of features to this problem we're going to have to analyze. First of all, we're talking about when the tank is full, so we've got to be concerned with volume. Also, we are told the rate of change of the volume, that coming in and that going out. Lastly, what we're asked about is the concentration of the additive in the tank. Let's set a few variables. First of all, V, as a function of t, is our volume. Next comes Q of t. That's the quantity of the additive that is put into the tank. So that when we talk about the concentration, C of t, that is simply Q of t over V of t. Let's derive the differential equation and then solve it. By considering flow rates coming in and out, it's easy to see that the volume is the initial volume, 900, plus 5t, meaning that the tank will be full at precisely t equals 20. If we consider the time rate of change of the amount of additive, Q, well, that additive comes in at a rate of 10 gallons per minute, but the fluid is drained out at a rate of 5 gallons per minute. That drained out fluid is not pure additive, but depends on the concentration, C. Thus, we derive a differential equation on Q as follows: dq dt plus Q over 180 plus t equals 10. This is a linear, non-autonomous ODE, where the function a is negative 1 over 180 plus t. That means our integrating factor is e to the integral of dt over 180 plus t. Of course, that integral is simply the log of 180 plus t, and when we exponentiate that, we obtain simply 180 plus t. If we therefore multiply the differential equation by this integrating factor, we obtain, very simply, 180 plus t times dq dt plus q equals 10 times quantity, 180 plus t. The left-hand side is the derivative of q times quantity, 180 plus t. Integrating both sides gives us on the left 180 plus t times q, on the right 1800t plus 5t squared plus a constant. You can show, based on the initial condition that there's no additive at the beginning, that that integration constant is 0. Now we almost have the solution to our problem. What do we need to do? We solve for Q as 1800t plus 5t squared over 180 plus t. But we're asked about the concentration at the time when the tank is full. At t equals 20, we get the amount of additive to be 190. Therefore, the concentration at that time is 190 divided by the volume of the tank. That means that the additive is present at 19% when the tank is full. There are many similar types of problems for which integrating factors are helpful. Some of them are like this, involving mixing and tanks. Others come from entirely different applications. And indeed, this is just the beginning of the wonderful subject of differential equations, where there are many more families of differential equations that require specialized solutions. A few of these are doable with the tools that you now have in hand, but many of these differential equations require multivariable calculus. Some can be very difficult to solve indeed.
We now have in hand several types of ODEs, their solutions, and their applications. That's the good news. The bad news is most differential equations are hard to solve. Some seem impossible. In our next lesson, we'll consider what to do when the solution seems to slip from our grasp.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 20 on ODE linearization.
Differential equations open up an entire world of applications of calculus. However, there are limits as to how far integration will get you. In this lesson, we'll explore those limits of integration and see what to do when integration doesn't work. Along the way, we'll learn how to linearize a differential equation.
We have seen in the past how to use calculus to linearize functions, but there are many other things that can be linearized. In today's lesson, we'll consider linearization of differential equations. We're going to do so through examining a simple model for a simple oscillator, by which I mean something that goes around and is periodic in its behavior. We're going to consider theta, an angular variable, as a function of time, and we want the simplest possible model. That is, theta simply evolves linearly over time from 0 to 2 pi and then back to the beginning. What kind of differential equation would model that? Well, I think you can figure that one out. d theta dt equals a constant. This has solution by integrating. Theta is at plus the constant of integration, the initial condition, theta naught. But notice that because we're interpreting this as an angle, everything is modulo 2 pi. When you get to 2 pi, you are reset to 0. What happens if instead of a single oscillator, we have a pair of simple oscillators? The first one, let's say, has an angle theta 1 of t. The second has an angle theta 2 of t. The differential equations would be simply d theta 1 dt equals a and d theta 2 dt equals a, where we assume that both oscillators have the same natural frequency, a, that determines how fast they spin. What happens, however, if we have these oscillators coupled, if they exert a mutual influence one on the other? That is, if theta 2 is a little bit ahead of theta 1, we want to add something to d theta 1 dt and subtract something from d theta 2 dt. Speed one up, slow the other down. This is going to be a small amount, a small coupling, and it's going to have to depend on the values of theta 2 and theta 1. The model that we'll use is adding or subtracting a small number, epsilon, times the sine of theta 2 minus theta 1. We use that expression to keep things angular. This quantity, theta 2 minus theta 1, has a name. It is called the phase of this pair of oscillators. It's the difference in angles. What we're going to do is consider how the phase evolves. How does it change? Well, to determine its rate of change, we compute the derivative, d phi dt, from the definition. That is simply the derivative of theta 2 minus theta 1. Now we know what d theta 1 dt and d theta 2 dt are from our model. It is a minus epsilon sine phi minus quantity a plus epsilon sine phi, where notice we've substituted in phi at the appropriate place in our model. There's some obvious cancellation that goes on, and we're left with negative 2 epsilon sine phi. Notice this is a differential equation that we can solve. d phi dt is negative 2 epsilon sine phi. So let's try to solve it and see what happens. If we use separation, we get d phi over sine phi equals negative 2 epsilon dt. And now we integrate both sides. What do we get? Well, on the right-hand side, we get, clearly, negative 2 epsilon t plus a constant. On the left-hand side, well, we need to integrate the cosecant. Integration can be difficult. This is one of the problems in differential equations. I don't remember the integral of cosecant. But let's say that I look that up, and I get that the integral of cosecant is minus log absolute value cosecant plus cotangent. Even when I have that, that does not help me. Hardly at all. I can write down that solution and exponentiate to get cosecant phi plus cotangent phi is a constant times e to the 2 epsilon of t. But what I want is to know phi of t, what the phase is doing as a function of time, and I cannot solve that equation for phi. What do we do when we can do the calculus but can't interpret the results? We're going to simplify through linearization, not linearizing a solution, but linearizing the equation itself. If we consider d phi dt equals negative 2 epsilon sine phi, and we expand that sine phi about phi equals 0, we can drop the higher order terms and keep only the linear term, giving the linearized differential equation d phi dt equals negative 2 epsilon phi. Now you know and I know the solution to such an equation depends on the constant in front. Therefore, we obtain the linearized solution given by the initial condition phi naught times e to the negative 2 epsilon t. This is only an approximate solution to the original differential equation, but this approximation gives us a hint. It predicts that there is an exponential decay in the phase. That is, if you have two oscillators with this coupling between them, then their angle difference, their phase, should be decreasing exponentially to 0. This is called synchronization. It says or predicts that these two oscillators will become in sync. Now, the wonderful thing about this is that you can observe this phenomena in simple physical systems involving oscillatory agents with a small amount of coupling between them, and you can see that they do synchronize. Once the synchronization occurs, it is fixed and it never changes. This is an example of something called an equilibrium solution. More generally, an equilibrium of the differential equation x dot equals f of x is a solution of the form x of t is a constant. Otherwise said, dx dt, or x dot, equals 0. Now, since x dot equals f of x, one could also define an equilibrium as a root of f, the right-hand side of the differential equation. Now, if you look at solutions to x dot equals f of x and plot them as a function of time, t, you will occasionally find some initial condition for which you have a constant solution. These are equilibria of the system. If you start there, you stay there. Now, these equilibria come in two forms in general. These are the stable equilibria and the unstable equilibria. A stable equilibrium has the property that if you have an initial condition that is nearby and you evolve it over time, you get closer and closer to the stable equilibrium. This is what we saw with the coupled oscillator with phi equals 0. On the other hand, there are unstable equilibria for which if you start at a nearby initial condition, you do not converge to the equilibrium solution over time. Rather, you diverge and move away. Now, one way to determine stability of an equilibrium is to plot not x versus t, but x dot versus x. Remember, x dot equals f of x in this model, and so by plotting f, one can see the equilibria clearly. The roots of f, that is where it crosses the horizontal axis, are precisely the equilibria. And looking at the graph tells you whether x dot is positive, that is, x is increasing, or x dot is negative, that is, x is decreasing. And so one can see the stable equilibria as things like sinks, where nearby values of x tend toward the equilibria. The unstable equilibria look like sources. Starting nearby pushes you further and further away. In the context of the system that we looked at, the phase equation, phi dot equals negative 2 epsilon sine phi. What did we see? If we plot phi dot versus phi, then we get a sine wave with a negative coefficient out in front of it. Notice that this has a root at phi equals 0. And when phi is less than 0, then phi dot is positive, and you're increasing phi as a function of time. To the right of 0, phi dot is negative, which means that phi is decreasing as a function of time. And this tells us that 0 is a stable equilibrium for this system. That means if you have no angle difference between the two oscillators, it will remain that way. If you have a small angle difference, well, it will disappear. And as we saw from linearization, that will happen exponentially fast. Notice, however, that this system also has another root, another equilibrium at phi equals pi, which is the same as negative pi. And this is unstable. Physically, this corresponds to an anti-synchronization, where the two oscillators are perfectly out of phase, where their angles differ by a value of pi. Now, we've seen how linearization was useful in predicting a stable equilibrium for our phase equation. How does linearization work in the general case where x dot equals f of x? Well, let's make an assumption that x has an equilibrium at A. Then, what happens if we Taylor expand the equation about this equilibrium? X dot equals f of x, but that is, as you know, f at A plus f prime at A times x minus A, plus some terms in big O of x minus A squared. Now, because A is an equilibrium, that means x dot equals 0 there. X dot is f of x, so f at A vanishes. That means we have x dot is f prime at A times x minus A plus higher order terms. To linearize, we drop the higher order terms and look at the coefficient in front of the linear term. This coefficient is f prime at A, the derivative of f at the equilibrium. Now, what does this mean? This means that if the derivative is positive at A, then what? Well, to the left, x dot is negative and is decreasing. To the right, x dot is positive and x is increasing. That means we have an unstable equilibrium if the derivative is positive. On the other hand, if the derivative is negative, if f prime at A is less than 0, then to the left, x dot is positive and x is increasing. To the right, x dot is negative and x is decreasing, and we have a stable equilibrium. This follows the exact pattern that we saw for our simple linear ODE. The sign of the constant out in front tells you whether you have exponential growth or exponential decay, whether you're unstable or whether you're stable. This technique of linearizing a differential equation about an equilibrium is a very powerful method, but is really just the beginning of the wonderful subject of dynamical systems, a qualitative approach to differential equations that works when an exact calculus-based solution doesn't. If you find this subject interesting, you may want to take a course on dynamical systems sometime after you've learned a bit more calculus.
Coupled oscillators provide a great example of the use of linearization in differential equations and dynamics. Head on over to the bonus material for this lecture, and we'll see if we can't get a couple of oscillators to synchronize.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 20, Bonus Material. In our main lesson, we analyzed the differential equations for a pair of coupled oscillators and showed that the phase, the angle difference between them, goes to 0, at least after linearization. Does this really work? Let's see.
Let's do an experiment. I've set up a pair of metronomes, each set to presto, or 184 beats per minute. We're going to couple these oscillators together by means of a common rolling platform. That way, as each metronome swings from one side to the next, it imparts an impulse that is communicated to the other oscillator. Let's set first one and then the other in motion, see if the phase difference between them decreases, and if so, we'll give it a little perturbation, see if it's stable. I think that worked pretty well.
Indeed, it certainly seemed as though we saw a wonderful example of a linearized solution, predicting exactly what was going to happen. But did we really see what we predicted? Let's take a careful look. If we look at a waveform analysis of the sound patterns that occurred, and we identify where the beats were, then you'll notice even after a long time to let the system stabilize, there's a little bit of a gap between the two clicks of the metronome. They didn't synchronize perfectly. It seems to be about 6/100ths of a second gap between them. Now, maybe we didn't let the system run long enough? No. Our prediction says that it's supposed to decay exponentially to a phase of 0. We shouldn't have such a stable gap. What might the explanation be? Well, we certainly made a number of assumptions in our model. One of the critical assumptions was that the frequencies of the two oscillators were identical. But what if they're not? I had to set the frequencies on those two metronomes by hand, and it's not likely that they were exactly the same. Let's rewrite our model to have a pair of frequencies. The first, A1, the second, A2. Then, repeating the derivation of the differential equation for the phase, phi, what do we get? Well, we'll get d phi dt equals A2 minus A1 minus 2 epsilon sine phi. If A1 and A2 were identical, then those terms would vanish as before, and the previous analysis would hold with a stable equilibrium at phi equals 0. However, in this more general case, when we set d phi dt equal to 0 and solve for the equilibrium, what do we get? We get that phi is arcsine of A2 minus A1 over 2 epsilon. If we, say, approximate that near 0, the first term in the Taylor series of arcsine would be A2 minus A1 over 2 epsilon. What does that mean? Well, that means that there's still an equilibrium in this system. And in fact, there's an equilibrium that is close to 0, but not quite 0. Depends on the values of A1, A2, and epsilon. It is still, however, a stable equilibrium. This slight change in our model predicts something like a synchronization, but for a phase that is not quite 0. That is exactly what we saw in our experimental data. Now, do note a few things. If your coupling strength, epsilon, is very small, if it's a weak coupling, or worse still, if the difference in frequencies is too large, then this arcsine might not give you an equilibrium at all. You might fail to have an equilibrium. You might get no phase locking or synchronization at all. There are so many other interesting phenomena that we could study by changing parameters. What happens if instead of 2 oscillators, we have 3? Will they synchronize together? Does it matter how we connect them up? If we tie them together along a line, or if we connect them all to all, does the influence patterns change the eventual behavior? What happens if instead of 2 or 3 oscillators, we consider yet more? What kinds of features can emerge from this system? Well, you're going to need something a bit stronger than single variable calculus to be able to handle thousands of variables. Now, you may wonder when you're ever going to run across thousands of metronomes that you need to analyze. But of course, this model applies anytime you have a collection of agents that are linked by some network. This is going to have applications in biology, in neuroscience, in behavioral science, anytime you have a network. And indeed, there are so many fascinating things that emerge when you start looking at behavior of a large number of agents. The simple things that we've done in differential equations just scratch the surface. For example, it's possible to have equilibrium solutions in a network of coupled oscillators that generate waves. It depends on the topology of the underlying network. That is, how are things connected up? Loops or large cycles, like you see demonstrated here, can give rise to very interesting behavior. But that's a subject for another course. Perhaps you'll take a course in dynamical systems at some point and learn how to study such systems. If you do, you're going to want to know not only single variable calculus, but multivariable calculus as well. Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 21 on substitution.
Now that we've seen what indefinite integrals are good for, differential equations, and more, we turn to the problem of the mechanics of integration. How does one compute an antiderivative? That is a large and convoluted subject. In this lesson, we'll begin with our first method, that of substitution.
Our first set of strategies for computing integrals exploits the fact that integration is anti-differentiation. Therefore, integration rules can be derived from differentiation rules. Let's consider, for example, the linearity rule for derivatives. What this tells us when we take those rules and then integrate them is that integration is also linear. The integral of a sum is the sum of integrals. The integral of a constant times an integrand is that constant times the integral. So, integration, like differentiation, is a linear operator, as you certainly already knew. Other differentiation rules lead to other integration techniques. We're going to focus on the chain rule, where tradition dictates the use of u as a function of x. In this case, the chain rule says that du is du dx times dx. We can integrate both sides. And after composing with a function f of u, then one obtains what is typically called the u substitution formula. Namely, the integral of f of u du is the integral of f of u of x times du dx dx. Now, of course, this u substitution formula is just the chain rule in reverse. However, it's very useful if you can determine what is u and what is f. Your goal is the integral on the left, the f of u du, which is hopefully simpler than what you are given on the right, the more complex-looking integral in terms of x. It's best to see this through a simple example. Consider the integral of e to the sine of x times cosine of x dx. You may or may not be able to see what the antiderivative is. However, if we let u be equal to sine of x, then du is cosine of x dx. We can see that e to the sine x is really just the exponential of u, whereas the cosine of x dx is the du term. Thus, by substitution, we can say that this integral is the same as the integral of e to the u du. Now, of course, we all know that the integral of e to the u is simply e to the u plus a constant. We're not quite done in that we need to substitute back in for a function of x. So our original integral evaluates to e to the sine of x plus a constant. Now, we could and should check that this is actually the correct answer. We should differentiate e to the sine of x and see that we obtain e to the sine of x times cosine of x dx. That's the wonderful thing about these types of problems. You can always check your results. Now, in this case, choosing the u and choosing the f were easy, almost transparent. This is not always the case. A trickier sort of example would be something like the integral of x times the square root of x minus 1 dx. In this case, what is the u here? What is f of u? In general, it's best to make a substitution that simplifies your integrand to whatever extent possible. In this case, if we were to let u be equal to x minus 1, It would seem to be trivial since du equals dx. However, notice what happens. X is u plus 1, and square root of x minus 1 is square root of u. We can therefore expand this integrand out as u to the 3/2 plus u to the 1/2. Notice we could not do that with x. Now we can easily integrate this to yield 2/5 u to the 5/2 plus 2/3 u to the 3/2. Substituting back in x minus 1 for u yields the answer 2/5 quantity x minus 1 to the 5/2 plus 2/3 x minus 1 to the 3/2 plus a constant. I'll leave it to you to check this. Another example that is perhaps not so obvious is the following. The integral of cosecant theta times cotangent theta, d theta. Again, in the absence of something obvious to do, try simplifying your integrand. In this case, using the definition of cosecant and cotangent yields cosine theta over sine squared theta, d theta. And now it's a bit more apparent which substitution to try. Let's try u equals sine theta. In this case, du is cosine theta, d theta, and we see the du sitting right in front of us. This becomes the integral of 1 over u squared times du. That we can certainly integrate to yield negative 1 over u plus a constant. Substituting back in, we get negative 1 over sine theta. That is negative cosecant theta plus a constant. I'll leave it to you to check. We're going to put these techniques to use in a differential equation that models the growth of a tumor. The Gompertz model for the size, n of t, of a tumor as a function of time, t, is the following differential equation. dn dt equals negative a times n times log of quantity b times n. Here a is a constant that is positive, and b is a constant that is between 0 and 1. Using the method of separation, we move all of the n's to the left-hand side, and we obtain dn over n times log of b times n. On the right-hand side, we're left with negative a dt. Now we need to integrate both sides of this equation. How do we perform the integral on the left? We're going to have to do a substitution. If we let u be log of b times n, then du is equal to dn over n. And we see that this integral is going to simplify dramatically to du over u. On the right-hand side, we again have the integral of negative a dt. Computing both the integrals gives us log of u equals negative at plus a constant. As with other equations we've done, we're going to exponentiate both sides to obtain an answer. U is constant e to the negative at. But we're not quite done, because u is not what we were looking for. We were looking for n. And so we must substitute back in for u. Log of b times n is constant e to the negative at. Now, to solve for n, we're going to have to exponentiate both sides again. Doing so, and dividing by b, gives us n, the size of the tumor, as a function of time t, is 1 over b times e to the constant times e to the negative at. This is a double exponential. It has an exponential in the exponent. Now, what about this constant c? I'll leave it to you to check that c is given as the log of b times n naught, where n naught is the size of the tumor at time 0. But deriving the solution is not the end of the story. We'd like to know something about how that solution behaves. Let's consider things from the point of view of equilibria. If we set dn dt equal to 0, what do we observe? We observe that there is an equilibrium at 0. Plugging in n equals 0 certainly gives dn dt equal to 0, as you can see by taking a limit. And it certainly makes biological sense that if the initial size of the tumor is 0, then no tumor will grow. However, there's another equilibrium at n equals 1 over b. In this case, that log term vanishes. What happens when we plot various solutions, n as a function of t? We see that the solution with a non-zero initial condition will converge to this 1 over b equilibrium. This is sometimes called the carrying capacity of the model. Now, indeed, if we plot n dot versus n, we will see these two equilibria arising, and we will see that 1 over b is a stable equilibrium, whereas 0 is an unstable equilibrium. This is what linearization will give. Now, the global perspective in what we have done in this lesson is all about this U substitution formula, but really, it should go under a different name, and you will learn it later in life under the name of the change of variables formula. What we're really doing is changing from x variables to u variables. And this change of coordinates facilitates integration. It makes it easier. For example, if we look at 2x sine x squared, then converting that over to sine of u makes something that's easily integrated to negative cosine of u, and then we go back to the original x coordinates. That allows us to compute a difficult integral by means of a simple integral in a new coordinate system. And that is the important point. Notice that as well we could run things backwards and obtain derivatives of complicated functions by a change of coordinates. That is what we did when we learned the all-important chain rule. Now, why is this perspective important? When you get to multivariable calculus, you are going to use a more sophisticated change of variables formula to solve some truly difficult integrals. Work now on the simple cases, and when you get to multivariable, you'll be fully prepared.
Substitution, or better yet, a change of variables, is one important method of integration. But it's merely the first in an increasingly intricate sequence of methods. In our next lesson, we'll introduce a second technique, that of integration by parts.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 22 on integration by parts.
We turn now to one of the best all-purpose methods for integration. This is the integration by parts formula. In this lesson, we'll learn what that is, why it works, and what to do if it doesn't.
Recall that our method for computing an integral as an antiderivative is to take a differentiation rule and run it in reverse. In this lesson, we'll consider the product rule. Recall, this states that d of u times v is u dv plus v du. Now, by integrating and rearranging this rule, what will we get? Well, if we integrate both sides, then on the left, taking the integral of the derivative of u times v yields, of course, u times v. On the right, we have the integral of u dv plus the integral of v du. This leads to the integration by parts formula. The integral of u dv equals u times v minus the integral of v du. Now again, as a reminder, u and v are functions of some third variable, say x, and the way that this is typically applied is that you are given one of these terms, let's say the integral of u dv, as your problem. And this is a hard integral, one that you're not sure how to evaluate. What the integration by parts formula does is gives you a hopefully easier integral in the form of the integral of v du. Let's look at this in the context of an example. Compute the integral of x e to the x dx. In order to apply the integration by parts formula, we're going to have to identify which term should be u and which should be dv. There are choices to be made. Well, let's proceed by taking a guess and seeing how it works. Let us choose as u x and as dv e to the x dx. This is going to be a pretty good choice in that when we compute du, we get something simple, dx. But when we integrate dv to get v, well, it's an integral that we can do. The integral of e to the x dx is, of course, e to the x. Now, in this case, why did we not choose a plus c, an integration constant? Well, let's see what happens when we apply the formula without that constant. The integration by parts formula says that the integral of x e to the x dx is u x times v e to the x minus the integral of v e to the x times du dx. And now you see how the formula is supposed to work. This rearrangement gives us a simpler integral to evaluate. Of course, we know that the integral of e to the x is just e to the x plus a constant. Now, I'll leave it to you to figure out why adding the single integration constant at the end suffices. We don't have to worry about it in the middle. Now, we should probably rearrange terms, simplify a little bit, to get a final answer of quantity x minus 1 times e to the x plus a constant. In this case, you should always check your answer to make sure that when you differentiate it, you get back the original integrand. For another example, compute the integral of log of x dx. In this case, the choice of u and dv is maybe not so obvious. In general, you want to keep things as simple as possible. Therefore, let u be equal to log of x, since we know how to differentiate that. Dv would necessarily be dx. Thus, computing du as 1 over x dx and v as simply x, the integration by parts formula says that the integral of log of x dx is u times v, that is x log x, minus the integral of v du. That is the integral of x times 1 over x dx. Notice how that is a simpler integral, yielding x log x minus x plus a constant. Or if we simplify, x times quantity log of x minus 1. Again, you'll want to check your work to make sure that the derivative of this is in fact what we began with, is the natural log of x. For another example, compute the integral of sine of x over x dx. Well, we have a couple of choices here. Let's try letting u be equal to sine of x and dv being 1 over x dx. In this case, du would be cosine of x dx, and v would be the antiderivative of 1 over x, that is, the natural log of x. The integration by parts formula gives what? U times v, that is, log of x times sine of x, minus the integral of v, log of x, du, cosine of x, dx. Well, this does not look so good. That second integral looks more difficult than the first. I think this counts as a failure. We chose our u and dv incorrectly. There's no guarantee that the integration by parts formula is ever going to work for any choice of u and dv. But let's try again. If we chose u to be 1 over x and dv to be sine of x dx, then, well, we can compute du as negative 1 over x squared dx, and we can antidifferentiate sine to get minus cosine. Applying the integration by parts formula with this choice yields what? U times v is negative cosine of x over x. Then we have to subtract the integral of v du. We get a cosine x over x squared dx. I think this again counts as a fail. That looks like a worse integral than what we started with. What does this mean? Have we chosen wrong? Is there another way to do this? Well, no. In fact, this is not an integral that has a simple representation for its antiderivative. In fact, we call the integral of sine of x over x the sine integral. It goes under the notation SI of x. It does not have a simple antiderivative. Sometimes the integration by parts method does not work for any choice of u and dv. Well, let's move on. Let's consider the integral of e to the x, sine of x. Let's let u be sine of x, dv be e to the x dx. Computing du as cosine of x dx and v as e to the x yields, by the integration by parts formula, e to the x sine of x, that's u times v, minus the integral of e to the x cosine of x dx. Well, again, this looks like one of those situations where this formula did not simplify things. However, we should not give up. Let's consider applying the method again to the integral of e to the x cosine of x dx. Let's choose our u to be cosine of x, dv to be e to the x dx. Then computing du and v, much as before, we can apply the integration by parts formula to this integral to yield u times v, that's e to the x cosine of x, minus the integral of v du. That yields a plus integral of e to the x sine of x dx. And what do we have? Oh dear, we have our original integral again, and it seems as though we are caught in a loop. This certainly seems like a failure. However, let's be careful. Let us call this integral of e to the x sine of x I. What have we computed? We have computed that this I is really e to the x sine of x minus some other integral. Let's call the integral of e to the x cosine of x j. Then what we've computed in our last attempt was that I equals e to the x sine of x minus j, and j equals e to the x cosine of x plus I. This is a system of two equations with two unknowns. Let's substitute the latter into the former. And what do we obtain? We get that I equals e to the x sine of x minus e to the x cosine of x minus I. Be careful with your signs. In this case, solving for I yields an answer. It yields 1/2 quantity e to the x sine of x minus e to the x cosine of x. So, with 2 applications of integration by parts, we can solve this problem. The moral is, don't quit too early. But this yields the question, how many times do we have to apply this formula in order to get an answer? Well, I have a bit of bad news for you. You don't know. There are examples where you have to apply this many times in order to get the correct answer. However, this might not be so bad. Sometimes one can obtain what is called a reduction formula. Let's look at an in-depth example. Consider the integral of x to the n cosine of x dx, where n is a positive integer. In this case, we're going to choose our u to be something that will simplify under differentiation. Let's let it be x to the n, so that dv is cosine of x dx. In this case, du becomes n times x to the n minus 1 dx, and v is, of course, sine of x. The integration by parts formula gives what? U times v, that's x to the n, sine of x, minus the integral of v du. That gives n times x to the n minus 1 times sine of x dx. Pulling out the n gives us something that is maybe a little simpler, but it's still of the form x to some power times sine of x. So let's try the general case of the integral of x to the n sine of x dx. We'll, again, apply the integration by parts formula and make the same choices as we did before, so that du is n x to the n minus 1 dx, and v is negative cosine of x. Applying integration by parts gives what? The integral of x to the n sine of x is x to the n times minus cosine of x plus the integral of n x to the n minus 1 cosine of x dx. And now we see something of the same form as what we began, but notice that the powers of x are reduced by 1. This allows us to get a reduction formula. Continuing, here is the crucial step. X to the n cosine of x dx integrates to x to the n times sine of x minus n times, well, let's see, if we take the integral that we had on the previous slide and use the second integration by parts application, we get quantity negative x to the n minus 1 cosine of x plus the integral n minus 1 times x to the n minus 2 cosine of x dx. This simplifies a little bit into a formula that looks somewhat complicated, but note, one ends with an integral of the form x to some power times cosine of x dx, where that power of x is 2 less than the original n that you began with. Likewise, if we compute the integral of x to the n sine of x and follow the algebra of substituting in the integration by parts formula that we derived on our last slide, what do we get? We get, in the end, an integral of x to the n minus 2 times sine of x dx. These final formulae are called reduction formulae. They take a difficult integral, something like x to the n cosine of x, and reduce it to a simpler integral, x to the n minus 2 cosine of x. By applying this inductively, eventually you get down to x to the 0 times cosine of x, or maybe x to the 1 times cosine of x, and these are solvable.
Integration by parts is one of the key tools for computing integrals. You're going to want to have that well practiced and memorized. But it's not the end of our techniques. In our next lesson, we'll present a technique of integration based on substitution, but tuned for trigonometric variables.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 23 on trigonometric substitutions.
In our lesson on integration by substitution, the question remains, which substitution should I make? Well, that's not always an easy question to answer. It's a bit of an art form to know exactly what to substitute. In this lesson, we'll focus on a class of integrals that are amenable to a trigonometric substitution.
Recall from a previous lesson that when we apply the substitution formula to compute an integral, we are typically going from the more complicated looking expression to the simpler looking expression. However, anytime you have an equality in mathematics, it's a road that runs both ways, and we could try exploiting it in the opposite direction. That is what we're going to do in this lesson. This type of substitution is especially useful with trigonometric functions. We'll look at a trivial example. Consider the integral of dx over 1 plus x squared. You may know this one already. Whether you do or whether you don't, consider the following substitution. We're going to let x be equal to tangent of theta. Notice we're not defining theta in terms of x. We're defining x in terms of theta. Then dx would be secant squared theta d theta. Unlike what we do when we perform u substitution, here we directly substitute these in, and we get the integral of secant squared theta d theta over 1 plus tangent squared theta. Now, of course, recalling that tangent squared plus 1 is secant squared, we obtain a secant squared in both the numerator and the denominator. These cancel, revealing the integral of d theta, which is simply theta plus a constant. Now, we have to substitute back in for x, which involves inverting that substitution. We obtain simply arctan of x. Now, the various trigonometric identities that you may have encountered in the past are what dictate these trigonometric substitutions. Some of these you're going to want to have memorized. Cosine squared plus sine squared equals 1, and the version with tangent and secant. Not all trigonometric identities need to be memorized, but the more you have in your head, the easier it will be to see which substitutions to use. Hyperbolic trigs are also useful, and you should at least have seen some of the basic simplification formulae for hyperbolic trigonometric functions. Let's compute some examples. Consider the integral of the square root of 1 minus x squared dx. Let's substitute for x the function sine theta, so that dx is cosine theta d theta. This yields the integral of the square root of 1 minus sine squared theta times cosine theta d theta. And now we see why this is the right choice for x, because using the fact that sine squared plus cosine squared equals 1, we can replace 1 minus sine squared with cosine squared, hence eliminating the square root to yield the integral of cosine squared. This, too, after a trigonometric identity, gives the integral of 1/2 plus 1/2 cosine 2 theta. This is something we can integrate. 1/2 integrates to 1/2 theta. 1/2 cosine 2 theta integrates to 1/4 sine 2 theta. Now, to substitute back in and obtain a function of x, what do? 1/2 theta becomes 1/2 arc sine of x. What about that second term? Well, we have a 1/4 times sine 2 theta. The double angle formula for sine allows us to replace this with 2 times 1/4 is 1/2 times sine theta, which is x, times cosine theta. What is cosine theta in terms of x? Well, if we set up a right triangle with an angle theta whose sine is equal to x, then we can read off the cosine from the Pythagorean theorem as square root of 1 minus x squared. This yields our answer, 1/2 arc sine of x plus 1/2 x times square root 1 minus x squared. For another example, consider dx over x squared times the square root of x squared plus 4. Which trig identity is going to be helpful here? I think that there was something involving tangents and secants that might allow us to get rid of that square root. So let's try x equals tangent of theta. Substituting in that and secant squared theta d theta for dx yields something that looks a bit complicated. Now, I hoped to use the fact that tangent squared plus 1 is equal to secant squared to eliminate that square root. However, I don't have tangent squared plus 1. I have tangent squared plus 4, and I can't eliminate that square root. What I should have done was chosen my coefficients more wisely. If instead of letting x be tangent theta, if we let x be 2 tangent theta, and replacing dx with 2 secant squared theta, that puts a 4 in front of the tangent squared terms. And now I can factor that 4 out from under the square root, obtaining a 2, canceling, simplifying a little bit. And now I can replace tangent squared plus 1 with secant squared and eliminate that square root. When I do so, I get 1/4 times the integral of secant squared d theta over tangent squared times secant. I can eliminate the secant in the numerator and the denominator and simplify what remains, rewriting in terms of sines and cosines, and we obtain 1/4 the integral of cosine over sine squared. Now, this integral is not going to be so bad. We've done something just like it before. We get, after substituting u equals sine theta, 1/4 the integral of du over u squared. This is negative 1 over 4u plus a constant. Substituting back in for theta, we get negative 1/4 cosecant theta plus a constant. Oh wait, we're still not done. We need our final answer in terms of x. So again, let's set up a right triangle, something for which the tangent of theta is x over 2. Then we can compute the cosecant of theta as square root of x squared plus 4 over x. Putting the minus sign in front and adding a constant gives us our answer. It is sometimes the case that a bit of algebraic simplification can reveal the appropriate substitution to be used. Consider the integral of dx over the square root of 3 plus 2x minus x squared. This seems completely opaque. However, if we use the method called completing the square, something wonderful happens. We're going to rewrite the term under the square root, negative x squared plus 2x plus 3, as negative quantity x squared minus 2x plus 3. Then we're going to turn the x squared minus 2x into a perfect square, rewriting that as x squared minus 2x plus 1. Of course, we're not allowed to stick in that plus 1 without compensating in what is left over. And keeping track of that minus sign, we get the equivalent expression 4 minus quantity x minus 1 squared. Now, rewriting our integral in this form gives us something a bit easier to work with. The first thing we're going to do is replace that x minus 1 with a u. Du is dx, and so we get simply the integral of du over square root of 4 minus u squared. And now the appropriate trigonometric substitution reveals itself. If we let u be 2 sine theta, then substituting in 2 cosine theta d theta for du, and performing a little bit of simplification yields a nice integral. We can use the fact that cosine squared plus sine squared equals 1 and factor out that conveniently located 4 under the square root to obtain the integral of 2 cosine theta d theta over 2 cosine theta. Those, of course, cancel and yield a trivial integral. Our answer is theta plus a constant. What is that in terms of u? That's just arcsine of u. What is that in terms of x? That is arcsine of quantity, x minus 1. That is a very simple integral that doesn't look anything at all like that integrand. Hyperbolic trigonometric functions are also very helpful. Consider an integral of the form dx over square root of 1 plus x squared. Now, we could have tried using a tangent and secant method. If x is tangent of theta and dx is secant squared of theta, d theta, then using the fact that 1 plus tangent squared equals secant squared and eliminating the square root gives the integral of secant theta d theta. And here I'm stuck. I don't remember how to integrate secant. It always seemed to me that it was a tricky sort of integral. Let's try a different approach. Consider x as the hyperbolic sine of u, so that dx is the hyperbolic cosine. Then this integral is equivalent to the integral of cosh u over square root of 1 plus sinh squared u. Now, keeping in mind that sinh squared plus 1 is cosh squared, this hyperbolic identity, we can eliminate the square root entirely, and we get cosh u over cosh u, which simplifies to the integral of du. That is, u plus a constant, or substituting back in for x, we get the arc hyperbolic sine of x. Wasn't that a simple integral to do? Now, if you pay attention, you see something a bit remarkable here, namely that the integral of secant, something that seems kind of difficult to derive, is in fact the arc hyperbolic sine of the tangent, substituting in tan theta for x. That's a non-trivial result. Now, of course, that's not the integral that you usually see in the back of the book. You usually see log of secant plus tangent. Both of these are correct and indeed equivalent. As a general bit of advice, when you see certain forms having to do mostly with square roots, then taking advantage of the appropriate trigonometric or hyperbolic trigonometric identity prompts a certain substitution, and these will often simplify your integral to something that is very doable. You don't have to necessarily memorize this table, but it's good to have done enough homework problems so that you get an intuition for which substitution is appropriate.
Trigonometric and hyperbolic trigonometric functions can be wonderfully useful in substitutions for solving integrals. However, some complexities can arise, as you'll see in the bonus material for this lecture. In our next lecture, we'll consider some methods of integration that are based more on algebraic manipulations.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 23, Bonus Material. In our main lesson, we gave a collection of substitutions involving trigonometric or hyperbolic trigonometric functions. These work great for computing some integrals, but at times you've got to be careful. Let's consider a simple example of a differential equation model that is amenable to a trigonometric substitution. Let's say that a financial model projects that your marginal profits are going to be a constant plus some term that is proportional to the square of the net profits. What do you think about such a model? Does that sound like a good investment? Well, let's translate what that model says into a differential equation. If P as a function of t is your net profit, then what do we mean when we say that the marginal profits are equal to a constant plus a term proportional to the square of the net? Well, the marginal profit is the derivative dp dt. To say that that marginal profit is equal to a constant, let's make sure that it's a positive constant by calling it b squared, plus some term proportional to the square of the net profits. Let's call that term a squared p squared, so that the constant of proportionality here is also positive, as it must be. Then, how do we solve this differential equation? If we perform substitution, then on the left, we need to compute the integral of dp over b squared plus a squared p squared. On the right, we have the integral of dt. Now, which trigonometric substitution is appropriate? Well, clearly, using a tangent is what we're going to want. So, let us substitute for p b over a times tangent of theta. dp is therefore a secant squared. Now, when we plug that in, well, we get b over a secant squared theta for dp, and in the denominator, b squared secant squared theta. The secant squareds cancel, the b's cancel, and we're left with d theta over a times b. Now that integrates to simply theta over ab. Setting that equal to the integral of dt, that is t plus a constant, allows us to very easily substitute back in for theta the arctangent. We therefore have t plus a constant equals 1 over ab times the arctan of a over b times p. Solving for p as a function of t after a little algebra yields b over a times tangent of quantity abt plus a constant. We can show, based on an initial condition, that that constant is, say, 0. Let's say we're starting off with no profit at all at time 0. Very good. We've got our answer, and we've done the mathematics correctly. But what do you think about this model for the net profit? Is it realistic? Well, what is happening to P as T increases from 0? Well, we're getting a tangent function, which means that at some finite time, T, the function is going to get very large. It's going to blow up to infinity. In fact, these are called blow-up solutions or singularities, and they arise sometimes when performing a trigonometric substitution based on the nature of the tangent, cotangent, secant, and cosecant functions. Now, you may think that such a solution to a differential equation is inherently non-physical. We don't have things going to infinity in a finite time. However, there are examples of physical settings where blow-ups or singularities in the differential equation are important to consider. For example, in certain areas of physics, one has a resonance phenomenon. Think of a vibration that is forced at a certain critical frequency that leads to feedback. This corresponds to a blow-up solution to the relevant differential equation, but it is not something ignorable. Indeed, one often has to engineer around such resonances for safety purposes. Other examples include vortices in fluid dynamics or in electromagnetics. These can arise as singular solutions to the relevant differential equations, and nobody would argue that things like tornadoes or hurricanes are unimportant or uninteresting. In fact, the differential equation that models three-dimensional fluid dynamics, that is, the Navier-Stokes equation, is a very fascinating set of equations. Unfortunately, we don't have enough calculus down as yet for us to be able to appreciate these equations fully in this class. However, it is an open problem in mathematics whether or not the solutions to these differential equations have finite time blow-ups or singularities in them. This is one example of a very simple sounding problem, which is nevertheless open and unknown to the best of mathematicians. Many very good mathematicians are currently working on this problem. After you've had a little bit of multivariable calculus, you might be able to work on it too. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 24 on partial fractions.
The previous 3 lessons have solved integrals by means of running differentiation rules in reverse. We're going to change our perspective now and give an introduction to methods based on algebraic simplification. The broadest and most generally useful such method is called the method of partial fractions.
In this lesson, we'll look at certain algebraic methods for simplifying integrands. Indeed, certain integrands respond well to a pre-processing step. This is especially true for rational functions, ratios of polynomials. For example, if you are asked to integrate 3x squared minus 5 over x minus 2, then naturally you would perform the polynomial division and rewrite this as 3x plus 6 with a remainder of 7 over x minus 2. And while the former integral seems intimidating, the latter integral is simple. 3x gives 3 halves x squared, 6 integrates to 6x, and 7 over x minus 2 yields 7 log x minus 2, and then add the constant. Now, this is a trivial example, but what happens when you have a higher degree denominator in your rational integrand? We're going to rely on a certain result from algebra, which states the following. A rational function, p of x over q of x, where the degree of the denominator is greater than the degree of the numerator, and for which the denominator has distinct real roots, r sub I. That is, we're looking at an integrand of the form polynomial p over x minus r1 times x minus r2 times etc., all the way up to x minus r sub n, where q has n distinct real roots. Then this can be factored or decomposed as a sum of constants a sub I over quantity x minus r sub I. This fact is something that we're going to take for granted. We're not going to prove it, but we're going to use it extensively. This integral of p over q seems very difficult in general. However, the right-hand side can easily be integrated since all of these a sub i's are constants. Then we get simply logarithms. Now, what do we do to come up with this decomposition? How do we determine these constants a sub I? This is sometimes called the method of partial fractions. Let's look at an example. Simplify 3x minus 1 over x squared minus 5x minus 6. We can factor the denominator as quantity x plus 1 times quantity x minus 6. By our algebraic fact, we know that this must be a1 over x plus 1 plus a2 over x minus 6. For simplicity, let's call these constants a and b instead. Now, to determine a and b, we're going to multiply out the right-hand side, put it over a common denominator, where we'll obtain a times quantity x minus 6 plus b times quantity x plus 1 in the numerator. And now we're going to expand that multiplication out and collect terms so that the first degree coefficient is a plus b, and the constant coefficient is b times 1 minus 6 times a. Now, these must match up with the coefficients of the numerator, 3x minus 1. If we have two polynomials that are the same, then all of their coefficients must match up. And so we see we are reduced to two equations in two unknowns, namely a plus b equals 3 and b minus 6a equals negative 1. Now we can solve such a linear system of equations for a and b. It might take a bit more work than I'm willing to put on this slide. So let me show you a more direct method for computing a and b. If, as before, we write out 3x minus 1 equals a times x minus 6 plus b times x plus 1. Then, instead of expanding and collecting, we can do the following. We can say this is a true statement, and it must be true for all values of x. Therefore, it must be true at x equals negative 1. What happens when we substitute that in? On the left, we get negative 4. On the right, we get a times negative 7 plus b times 0. And we've eliminated that variable from consideration. Solving we obtain a is 4/7. Likewise, if we substitute in x equals 6 into the above equation, we get on the left-hand side 17. On the right-hand side, a times 0 plus b times 7. We therefore have eliminated a, and we can conclude that b is 17/7. And I'll let you check that these two satisfy the two equations in the lower left-hand corner. Now, let's put this method to work. Compute the integral of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. Factoring the denominator gives us x, quantity 2x minus 1, quantity x plus 2, all multiplied together. Now, we hope to split these up into a over x plus b over 2x minus 1 plus c over x plus 2. Let's color code these and then multiply everything out and see what we get. A times 2x minus 1 times x plus 2 plus b times x plus 2 plus c times x times 2x minus 1 must equal the numerator of the integrand, x squared plus 2x minus 1. Let's use our direct method of substitution. First, we'll substitute in x equals 0. When we do that, we eliminate all of the terms except the one involving a. We obtain negative 2a equals minus 1. Solving, we get a is a half. Likewise, if we substitute in x equals 1/2, we eliminate all the terms except for the b, which we solve to get b is 1/5. What's our last root? If we substitute in x equals negative 2, then we obtain a value for c of negative 1/10. Substituting these coefficients back into the integrand gives us, for our integral, the integral of 1/2 over x plus 1/5 over 2x minus 1 minus 1/10 over x plus 2. These are all going to be logarithms. We're going to get 1/2 log of x plus 1/10 log of 2x minus 1, being careful with that 1/2 coefficient, minus 1/10 log of x plus 2. Let's put this to use in a differential equation. Consider the deflection, x, as a function of time, t, associated to a thin beam that we've applied a force to. The question is, how does this deflection evolve? Well, if the load is proportional to a positive constant, lambda squared, then one simple model for this beam would be dx dt equals lambda x squared minus x cubed. We can factor that as x times lambda minus x times lambda plus x. And now, applying the separation method, we get on the left dx over x times lambda minus x times lambda plus x. On the right, dt. Integrating both sides prompts the use of a partial fractions method. I'll leave it to you to show that the coefficients in front of the terms are, respectively, 1 over lambda squared, 1 over 2 lambda squared, and negative 1 over 2 lambda squared. So that when we perform the integral, we get a collection of natural logs with coefficients in front, namely log of x minus 1/2 log of lambda minus x minus 1/2 log of lambda plus x equals lambda squared t plus a constant, where I've moved the lambda squareds to the right-hand side for simplicity. Now, what we would do next is try to solve for x as a function of t. This looks like it's going to involve a lot of algebra, and I'm not really in the mood. So let's use linearization and solve for the equilibria to see if we can understand what's happening. If we plot x dot versus x, we see that there are three roots. One root at 0, one root at negative lambda, and one root at positive lambda. By looking at the sign of x dot, or by linearizing the right-hand side of the equation, we can see that 0 is going to be an unstable equilibrium. That makes physical sense. If you're compressing the beam, if it were perfectly symmetric, then it would not deflect. However, that situation is inherently unstable. And if you start off with just a little bit of deflection in either direction, you will quickly move to one of the stable equilibria at lambda or negative lambda, depending on which side you buckle. Now, there are some complications involved with applying the method of partial fractions. We've assumed the existence of real, distinct roots. That is a bit of a luxury. In general, you don't have that. Sometimes you have repeated roots, something of the form a polynomial over x minus a root r to the nth power. This decomposes, but it decomposes into something a bit more complicated. There are n terms. Each is a constant over x minus r to some power, ranging from 1 up to n. Now, all of these individual terms are integrable, but some might take a little more work than others. What is potentially worse is complex roots, where you don't necessarily have real roots. Let's say we look at a polynomial over a quadratic, ax squared plus bx plus c. Then if the discriminant, b squared minus 4ac, is negative, we have complex roots. This does break up, but it breaks up into a linear polynomial in the numerator, and then the quadratic in the denominator. And if you have repeated complex roots, well, then it gets even more difficult still. All of these examples are doable, but very cumbersome, and I'm not going to test you on these in this course. In the end, it's really just algebra. And in the end, it's really just roots. The roots control everything, whether they're real, whether they're complex, whether they're distinct or repeated. As we saw in the example of the buckling beam, the roots have physical interpretations in differential equation models. Always pay attention to your roots, not just in calculus when trying to solve an integral, but in differential equations, or even later still, when you take linear algebra, you will see that the roots influence everything.
We've seen in this lesson how algebraic methods can be incredibly helpful and incredibly complicated. We're not going to descend any further into that underworld of integration techniques. Rather, we're going to turn our gaze to a new character in our story, that of the definite integral.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 24, Bonus Material. Let us consider a differential equation model for population dynamics. This time, a model that's a bit more sophisticated than the Malthusian model of exponential growth without bound. This is the so-called logistic model, and it states that the rate of change of a population size, p, is proportional to p by some constant, r, the reproduction rate. But there's another term on the right-hand side as well. This is negative c times p squared. That is, there is a death rate, c, that operates in front of a quadratic term in p. Now, if we were to factor this right-hand side, pulling out c times p, and having left over a constant kappa minus p, then, of course, this kappa would be the ratio of the reproduction rate to the death rate, r over c. Factoring in this way is going to allow us to apply the method of partial fractions. For when we do separation, we get, on the left, dp over p times kappa minus p, and on the right, c. Integrating both sides and applying the method of partial fractions to the left-hand side, we get a decomposition of 1 over p times kappa minus p as 1 over kappa times 1 over p plus 1 over kappa times 1 over kappa minus p. Now, what happens when we perform the integral? Well, on the right-hand side, we have the integral of c dt. Let's move the kappa over there, multiplying both sides of the equation by that constant, and then reducing c times kappa to r, so that on the right-hand side, we get rt plus a constant, and on the left-hand side, we get log of p minus log of kappa minus p. Now, when we go to solve this, we're going to have to do a bit of algebra, combining those logarithms together, and then exponentiating both sides gives p over kappa minus p equals e to the rt plus a constant. We can, by the usual trick, pull that constant out in front, from which we see that the constant is equal to the initial population, p naught, over kappa minus p naught. That's what we get evaluating at t equals 0. Now the only thing that's left to do is a bit of algebra to solve for p. When we do that, multiplying through and expanding out the multiplication, we collect terms on the left, and with a little bit of effort, we see that p is kappa times c e to the rt over 1 plus c e to the rt. Substituting in our value for the constant c and simplifying gives a final answer of kappa p naught over quantity kappa minus p naught times e to the negative rt plus p naught. That looks a bit complicated. Let's think about what is happening. Let's let t go to infinity and see what happens to the population size. Does it grow without bound? At what rate does it grow? Well, it's pretty obvious that this has a finite limit. In fact, if we set the right-hand side of the differential equation equal to 0 and solve for the equilibria, we see that there's an equilibrium at 0 and an equilibrium at kappa. And indeed, taking the limit of our explicit solution, we can see that as long as your initial condition is non-zero, the solution tends to kappa. We can see this easily if we plot p dot versus p. This is a quadratic with the coefficient in front of the quadratic term being negative. It definitely passes through the origin and it crosses the horizontal axis at kappa. Therefore, we see that kappa is a stable equilibrium and 0 is an unstable equilibrium. This, then, gives us a natural interpretation of this equilibrium solution, kappa, One calls this the carrying capacity of the model. It says that with this quadratic death term involved, then the population can only reach the carrying capacity. Now, this, again, is reminding us to pay attention to the roots. For the case of our differential equation, knowing those roots gives us the equilibria. Of course, in more generality, there are lots of other circumstances in mathematics where it is the roots that determine everything about the system. Although solving this differential equation took a lot of algebra, determining the behavior of these solutions as time goes to infinity was relatively painless, thanks to equilibria and linearization. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 25 on the definite integral.
In this lesson, we'll turn our attention from the indefinite integral, a class of functions, to the definite integral, a numerical quantity. No doubt you've seen definite integrals before, but do you remember how they're defined and what they really mean? This is one of those concepts that takes a few readings to really sink in. In this lesson, we'll give you a fresh look at the definite integral.
This lesson is all about adding larger and larger numbers of smaller and smaller local amounts into some global sum. That's not too unusual of a thing to do. So let's do so in the context of a simple classical example. Compute the sum I goes from 1 to n of I. That is 1 plus 2 plus 3, all the way up until n. Now we could think about this a bit more globally or geometrically by representing each I as a column of I squares, each with side length 1. The net sum then looks something like a triangle with base n and height n, but is discretized into these squares. What is the sum represented as an area? Well, the area of the triangle would be 1/2 n times n. But this ignores a few small leftover triangles, each with area 1/2. How many are there? Well, of course, there are n such leftover triangles. That yields a net area of 1/2 n times n plus 1. Now, if we think about what it would take to add up 1 plus 2 plus 3, all the way up until n, these are local additions or local computations. On the other hand, this general formula as a function of n is something that is more global. And that's really the key intuition behind what we're about to build. That is, the definite integral. The definite integral is a generalization of this kind of reasoning to more difficult or nonlinear sums. The definition of the definite integral is a little bit involved, so stick with me and review again as necessary. We write the integral of f of x dx as x goes from a to b as a certain limit. But what is that limit? How do we set it up? Well, first, we restrict to the interval from a to b. And then we build a partition. That is, we split this interval up into subintervals, p1, p2, all the way up to pn, that fill up the domain from left to right. Now, each subinterval has a width associated to it. This is called delta x sub I. Within each partition element, we choose a point x sub I that is within p sub I. This is called a sampling. Now, it doesn't matter which point you choose. Just pick one. one per subinterval. Then, we first define the Riemann sum to be the sum, as I goes from 1 to n, of f evaluated at the sampling point times the width, delta x sub I, of the partition element. This Riemann sum is often visualized in terms of columns or rectangles sitting over top of the partition. Then, with this in mind, the definite integral is defined to be a limit of Riemann sums, where it's an unusual sort of limit. We're taking the limit as the partitions get smaller and smaller, as the widths of the partition elements goes to 0. Now, you can see that as those widths get smaller and smaller, the dependence on the sampling seems to be less and less important. And indeed, that intuition does hold true. Now, there's a little bit of notation that goes into this. First of all, you should notice that that integral sign is really a form of the English letter S, in the same way that the summation sign is a form of the Greek letter sigma. Both connote a sum. So a definite integral is really a sum, and all of the notation associated with it matches the corresponding notation in the Riemann sum, where dx is something like the limit of delta x, as delta x is going to 0. Now, the second thing to note is the limits of integration. One often writes the integral from a to b of f of x dx. I prefer to write the integral as x goes from a to b of f of x dx. This tells you exactly which variable you're talking about in terms of the limits. I'm not always going to use that notation, but I will sometimes, and I suggest you do likewise. Sometimes we'll be sloppy and just write the integral from a to b. Lastly, the variable with which you do the integration is not so important. The integral of f of x dx, as x goes from a to b, is the same as the integral of f of t dt, as t goes from a to b. One could use other symbols still. What matters is the value of the integral, not the name of the variable with which you integrate. Sometimes we'll just write the integral of f from a to b, if it's clear which variable we mean. Let's do an example. Compute the definite integral of x dx as x goes from 0 to 1. From our definition, this is a limit of Riemann sums over partitions as the partition elements go to 0 in width. Now, since f of x is equal to x, that Riemann sum is just the sum of x sub I times the width delta x sub I. Let's choose a particularly nice partition, one which is uniform. That means the widths are a constant. Explicitly, we're going to set p sub I equal to I minus 1 over n to I over n. This subinterval is going to depend on n, and so we'll have a sequence of partitions. Now we need to choose a sampling point, 1 x sub I, in each p sub I. For simplicity, let's just choose the right-hand endpoint, I over n. Then the width, delta x sub I, is a constant, 1 over n, because we have a uniform partition. Therefore, the Riemann sum can be expressed as a limit as n goes to infinity. That is, as the widths are going to 0. What's the Riemann sum look like? It looks like the sum. I goes from 1 to n of x sub I, that's I over n, times the width, 1 over n. Now, what's this limit going to look like? Well, we're summing over I, and n is a constant. Therefore, we can factor a 1 over n squared out of the sum, and we're left with the sum as I goes from 1 to n of I. And now comes the hard part. Fortunately, we've seen that sum before. What's the sum? I goes from 1 to n of I. Well, that's really 1/2 n times n plus 1. And now we see that dividing by n squared, the leading order term in this Riemann sum is 1/2. Everything else is higher order in 1 over n, and hence goes to 0 as n goes to infinity. The answer to this definite integral is 1/2. Indeed, as it must be. Do notice that the difficult part of this computation was that sum of I as I goes from 1 to n. Note also that the definite integral satisfies certain properties. For example, linearity. If you have the integral of the sum of two functions, f and g, then it's really the sum of the integrals. Otherwise said, if you add your two integrands together and then integrate, you get the same thing as if you integrate the pieces and then add them together. This is true at the level of an individual Riemann sum element, and so it's true in the limit. Likewise, if you multiply an integrand f by a scalar c, then the integral is equal to that constant c times the integral of f. Again, otherwise said, you can multiply by a constant and then integrate, or integrate and then multiply by a constant. It doesn't matter. You get to the same place, whichever path you take. Again, the reason why this is true is because it's true at the level of Riemann sums, and hence in the limit. Another important property is that of additivity, which states that if you take the integral of f from a to b and add to it the integral of f from b to c, because those limits match up, you get the integral of f from a to c. This certainly makes sense at the level of a Riemann sum. You can concatenate these intervals together. We're going to think of it in terms of adding paths together, a perspective that makes sense in the context of orientation. That is, the integral of f from a to b is minus the integral of f from b to a. Now, why does this happen? Well, let's think of the following terms. If we were to move the integral from b to a over to the left-hand side of the equation, we would get that the integral from a to b plus the integral from b to a equals 0. Why would that have to be true? Well, from additivity, the limits match up and give us the integral from a to a, which clearly must be 0. That's one way to make sense of this orientation property. Another way to think about it is that we are adding directed paths together. And when you have the same path from A to B with the orientations reversed, it's as if the paths cancel, and you wind up getting the integral over a point, which is 0. The last property we'll discuss is that of dominance. That states that if f is a non-negative function, then the integral of f over an interval is also non-negative. From that follows a slightly less obvious result, namely if you have a function g, which is bigger than f, then g minus f is non-negative, which means that the integral of g minus f is non-negative, which by linearity means that if g is bigger than f, then the integral of g is bigger than the integral of f. So much for the good news. The bad news is we can hardly compute anything with this definition. There are two definite integrals we can compute. We can compute the integral of a constant by, let's say, choosing a uniform partition and then taking the appropriate limit. You can see that you get, a constant times the width of the interval. The other integral that we can do is the one that we've done already, the integral of x dx. If we do that over a general interval from a to b, then I'll leave it to you to set up the uniform partition, reduce it to a limit, and get the answer, which is, as it must be, 1/2 times quantity b squared minus a squared. That's about it. There's a little bit more that we can do. For example, if we tried to integrate sine of x or cosine of x, not over an arbitrary interval, but over a symmetric interval from negative L to L, then there are a few things we would observe. For sine, there's a symmetry about the origin, which implies that every time you have a partition element on the right, with say a positive value, you get a corresponding partition element on the left with the opposite value. These two will cancel and will give you an integral of 0 because sine of negative x is minus sine of x. For cosine, we can't quite do the same thing, but we have a symmetry about the y-axis, which means that every time you have a partition element on the right, it is balanced by a symmetric partition element with the same value of cosine. Therefore, we get a doubling. Because cosine of negative x equals cosine of x, we can reduce this integral to one from 0 to L and double it. This simple example has a more general pattern. We say that sine is an odd function and cosine is an even function. An odd function is one that has this symmetry about the origin, or a function for which f of minus x is minus f of x. For such a function, the definite integral over a symmetric domain from negative L to L is always 0. Likewise, for an even function, when f of minus x is f of x, then the integral from negative L to L is twice the integral from 0 to L. Another way to think about odd and even functions is that the odd ones have an odd Taylor series, and the even ones have an even Taylor series, all about 0. Now, in general, you're going to have to be careful. Definite and indefinite integrals are not the same type of object, even though they have similar notation. A definite integral is a number and a limit of sums. The indefinite integral is an antiderivative and a class of functions. We'll soon see what they have in common.
So what do you think of the definite integral? It's not so easy to compute, is it? The definition of the definite integral is like the definition of a derivative. It's crucial, it's complex, and it's quickly forgotten. Don't forget this definition. It's important. Fortunately, we won't have to use the definition to do computations because of what we'll learn in our next lesson, the fundamental theorem of integral calculus.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 26 on the fundamental theorem of integral calculus.
Based on the definitions alone, definite integrals and indefinite integrals seem to have nothing in common except the name and that long squiggly sign that we use to denote them. In fact, they are closely related. They are two aspects of the same character. We will see that in today's lesson, where we introduce the fundamental theorem of integral calculus.
The goal of this lesson is to understand and use the fundamental theorem of integral calculus. And while you've probably seen it before, a theorem of this importance is worth your careful attention. The fundamental theorem gives an equivalence between definite and indefinite integrals, specifically for f, a continuous function, on the interval from a to b. the definite integral of f of x dx as x goes from a to b is equal to the indefinite integral of f evaluated from a to b. Now again, these are ostensibly different objects on the left and the right-hand side. The definite integral is a number. The indefinite integral is a class of antiderivatives. The equivalence comes from the fact that we evaluate those antiderivatives at a and b. Another way to write this is more illustrative. The definite integral, as x goes from a to b, of df, where capital F is some function, is that antiderivative f evaluated from x equals a to b. Now this is a more compact way to write the result. In practice, you're going to want to think of it expanded out a little bit. Through the chain rule, df is really df dx dx, and that definite integral from a to b is simply the antiderivative f evaluated at b minus f evaluated at a. Now, this is not a new idea to you. You've certainly used this result before. We've certainly observed it, if nothing else, when we did the definite integral of x dx as x goes from a to b. By computing the Riemann sum, we found that the answer was 1/2 quantity b squared minus a squared. If we apply the fundamental theorem of integral calculus, what it says is that we can compute the antiderivative of x, which is, of course, 1/2 x squared, and then evaluate that at a to b. First, we plug in b and obtain 1/2 b squared. Then we subtract what we get when we plug in a, namely 1/2 a squared. And that, of course, is the same answer that we obtained earlier through more difficult means. This is the value of the fundamental theorem. It makes computations simple. Let's look at a different example. Compute the definite integral as x goes from 1 to t of 1/x dx. Now, we can think of this geometrically in terms of limits of Riemann sums, getting something that approximates the area under the curve 1/x. By the fundamental theorem, we can antidifferentiate 1/x to get, of course, log of x, and evaluate that from 1 to t. That gives us log of t minus log of 1. Of course, the natural log of 1 is 0, and so we obtain log of t as the answer, which gives us a new interpretation of the natural logarithm that you may have already known, namely that it is the area under the curve 1/x as x goes from 1 to t. Now this is all well and good, and you will find the fundamental theorem to be extremely useful in computations, but you must know what this theorem really means, and it has several interpretations. Let's look at the compact form of the fundamental theorem and rearrange the terms a bit, so that on the left we have a function f evaluated from a to b. That is equal to, on the right, the definite integral from a to b of df. Otherwise said, the net change in some quantity, f, is equal to the integral of its rate of change. Now you might say that's obvious, but it's not. And there are many different contexts in which this applies in a non-trivial and non-obvious way. Some are simple in saying that the position is equal to the integral of the velocity. or the net change in height, is equal to the integral of the growth rate. Some are not so obvious, particularly in economics, where one talks of marginal quantities as the derivative. So the net change in supply is equal to the integral of the marginal supply, etc. Let's do an example of marginal quantities. Let's assume that a publisher is printing 12,000 books per month with an expected revenue of $60 per book. But it costs money to publish these books, and the marginal cost is a function of X, the number of books published per month. This function is given by 10 plus X over 2,000. Then, what change in profit would result from a 25% increase in production? Let's set this up as an integral problem. First, we're going to need some variables. The cost element, that is, the rate of change of cost to the publisher, is given by this marginal cost function, MC of X, times dx, the rate of change of the number of books. This is, of course, 10 plus X over 2,000 times dx. What about revenue? Well, the revenue element, that is the rate of change of revenue, is given in terms of a marginal revenue function times dx. What is this marginal revenue function? Well, if we look at the problem, we see that the revenue is at $60 per book. Since it's a per book quantity, it is marginal. So the revenue element is 60 dx. Now the problem is asking for profit, in particular change in profit. And so we would look at the profit element, dp. P is for profit. This is the revenue minus the cost, or at the marginal level, the marginal revenue minus the marginal cost. This is 50 minus x over 2,000 dx. That is our profit element. And so, to obtain a net change in profit, what do? We integrate the profit element, 50 minus x over 2,000 dx, with what limits? Well, we began at x equals 12,000 books per month, and we need to get an upper limit. We were asked to consider a 25% increase in production. That would be going to 15,000 books per month. And so we see that the answer is a simple integral. We can do that antiderivative easily. 50 integrates to 50x. X over 2,000 integrates to x squared over 4,000. Subtract and evaluate as x goes from 12,000 to 15,000. I'll leave it to you to determine the numerical answer of almost $130,000. That is the net increase in profit. Let's consider another example, one that illustrates how we have to be careful with limits when applying integration techniques. Let's consider the integral as x goes from 0 to 1 of x times x minus 1. Well, no, that's too easy. Let's say x times x minus 1 to the nth power dx, where n is some positive integer, let's say. Well, one way to solve this would be by substitution, letting u be x minus 1. du is equal to dx, and so we obtain, simply, the integral as x goes from 0 to 1 of quantity u plus 1, that's x, times u to the n du. Now notice how I wrote in the limits x equals 0 to 1. but we're integrating with respect to u. Be careful with your limits so you know which variable you're talking about. Well, let's proceed. The integral of u plus 1 times u to the n du is, expanding, the integral of u to the n plus 1 plus u to the n du. That's a simple integral. That gives us u to the n plus 2 over n plus 2 plus u to the n plus 1 over n plus 1. And we need to evaluate that antiderivative as x goes from 0 to 1. But that's in terms of x. So, to compute the answer, we could substitute back in x minus 1 for u. This gives us x minus 1 to the n plus 2 over n plus 2 plus x minus 1 to the n plus 1 over n plus 1. Evaluating as x goes from 0 to 1 gives minus negative 1 to the n plus 2 over n plus 2 minus negative 1 to the n plus 1 over n plus 1. With a little bit of simplification, factoring out a negative 1 to the n plus 2, and then simplifying that to negative 1 to the n, we get our final answer of negative 1 to the n over n plus 1 times quantity n plus 2. Now, you can see how you could get into trouble if you weren't careful labeling the x limits versus the u limits. Now, another way to do this would be to change from x limits to u limits. When x is 0, u, x minus 1, is negative 1. When x is 1, u is equal to 0. By changing the limits to u limits directly, we can obtain the same answer very simply, and in some cases without the opportunity for confusion. Now, that's not the only way to solve this integral. We could have used the integration by parts formula. If, in this case, we let u be x and dv be x minus 1 to the n, then setting du equal to dx and v equal to x minus 1 to the n plus 1 over n plus 1, what do we obtain? Well, we get u times v, that is x, times quantity x minus 1 to the n plus 1 over n plus 1, minus the integral of v, x minus 1 to the n plus 1 over n plus 1, times du, that is dx. And that's a simple enough integral to do. However, we must be careful with the limits. The integration by parts formula for definite integrals follows the pattern you would expect, but you have to evaluate the uv term from a to b. So let's do so in this case, evaluating as x goes from 0 to 1. What does this give? Well, when we evaluate the u times v quantity from 0 to 1, we get at 1, 0. At 0, 0. That's simple enough. Fortunately, it goes away, and we're left with the integral of x minus 1 to the n plus 1 over n plus 1. That is, of course, x minus 1 to the n plus 2 over n plus 2 times that negative 1 over n plus 1 that was hanging around. Evaluating that from 0 to 1 gives us our answer very simply. Negative 1 to the n plus 2 over quantity n plus 1 times n plus 2. Pulling out a negative 1 squared gives us the same answer that we saw before.
The fundamental theorem of integral calculus is fantastic. With it, you're going to be able to compute definite integrals galore. With it, we're going to fuel all of the applications that we'll see in Chapter 4. But in our next lesson, we'll see that when pushed to the limit, this theorem can run into problems.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 26, Bonus Material. In our main lesson, we covered the fundamental theorem of integral calculus. And we saw how it was used and what it meant, but we did not say why it is true. Let's sketch a proof. But how do we proceed? Our goal is to show that the definite integral of f from a to b is the indefinite integral, evaluated at the limits. We won't prove that directly. Rather, we will prove a lemma, a preparatory step. The lemma is going to look very different, but is really closely related. It states the following. The integral of f of t dt as t goes from a to x is what? Well, let's see. This is going to be a function of x. If we differentiate that with respect to x, what will we get? We will get f of x, the integrand, evaluated at x. Now, this seems a little unusual since you're differentiating a limit of a definite integral. But let's explore, see if we can make sense of it. Let's make sure we're not completely crazy and check that this works in a simple case. Let's differentiate the integral as t goes from a to x of a constant dt. Well, we can do the definite integral of a constant c. That's just going to give us c times the upper limit x minus c times the lower limit a. If we differentiate that function of x, what do we get? We get c, the constant, which is the integrand we began with. So this is not a clearly crazy thing to do. Well, let's see if we can prove this lemma. Consider what the integrand f of t looks like. We need to compute the definite integral from a to x. And the claim is that the derivative of the definite integral is f evaluated at x. Well, let's see. Let's denote by capital F the definite integral as a function of x. Then, if we want to differentiate that with respect to x, what should we do? Let's look at what happens when we increase x by a small amount. Let's call that h. Well, according to the definition, that is the integral of f of t dt as t goes from a to x plus h. Now, of course, we could write that as the integral as t goes from a to x plus the integral as t goes from x to x plus h. That comes from additivity of the integral. And since, by definition, the integral from a to x is simply capital F at x, we see something that should start looking like the definition of a derivative, namely capital F at x plus h equals capital F at x plus something. What is that something? That something is going to have the derivative of capital F built into it. Now, what we need to focus on is this interval from x to x plus h. And here, I'm going to have to make a little bit of a more restrictive assumption about the integrand f, namely that not only is it continuous, but it also is reasonable. Let's say has a Taylor series associated to it. Now, for this definite integral, let's choose a partition with width h. What is the height? Well, the height, if we chose the left-hand endpoint, would be f of x. And the width is h. Now, this is not exactly what the definite integral is. It's just an approximation. There's some leftover stuff that we haven't accounted for. How can we estimate that? Well, if the integrand f has a reasonable form to it, let's say has a well-defined derivative in the sense of a Taylor series, then this change in the height, this change in little f, is going to be big O of h. That is, it shrinks to 0 linearly as h goes to 0. So the worst thing that could happen, the estimate for what we have left out here, is something that is big O of h times the width, h. Now, if we take big O of h times h, of course, that's big O of h squared. And now, stepping back, we see that we've computed the derivative of capital F of x, because capital F of x plus h is capital F of x plus something times h, plus something in big O of h squared. What is that coefficient in front of the h term? That first order variation is little f evaluated at x. That is what we're trying to prove. And now let's see what that does for us. The indefinite integral of f is what? Well, from this lemma, we see that the definite integral of f of t dt, as t goes from a to x, is an indefinite integral because its derivative is little f of x. Therefore, the general indefinite integral of f is this definite integral of f of t as t goes from a to x plus an arbitrary constant. We now have an explicit form of the antiderivative in terms of a definite integral. Now, what do we have to do? Well, if we were to evaluate that indefinite integral as x goes from a to b, what would we get? We would get the integral from a to x of f of t dt plus some constant c evaluated at b minus the same thing evaluated at a. Let's fill that in. When we evaluate at b, we get the integral of f of t dt as t goes from a to b plus a constant. We subtract off the integral as t goes from a to a of f of t dt plus a constant. I'm going to ignore the plus c because we first add it and then subtract it. Now, what do we notice? Well, the integral from a to a is always 0, and so we are left with the integral from a to b. But notice that we're using t, whereas we stated our theorem in terms of x. But of course, that doesn't matter a bit. You can use any symbol you want for the definite integral. And that is exactly what we were trying to show, that the indefinite integral evaluated from a to b is the definite integral from a to b. Well, that's nice as a proof. But one of the wonderful things about this proof is that it gives us a new tool for computing some interesting derivatives. Derivatives of definite integrals with functions in the limits. Let's do a more complicated example. Consider the derivative with respect to x evaluated at x equals 1 of the following function, the integral of e to the t squared dt, as t goes from log of x to square root of x. Now this, ostensibly, is difficult. You can't find the antiderivative of e to the t squared easily, if at all. But we can still compute this derivative. How do we do that? Well, we've got to be a bit careful. Our lemma only applies in the case where the limits are from a to x. And here we have functions of x. So let's think for a moment. What we know is that the derivative, the integral from a to x of f of t dt, is f of x. What is going to help us is to have the function of x at the upper limit. So let's rewrite this integral using additivity as the integral from 1 to square root of x plus the integral from log of x to 1. And now, using the orientation property, we can reverse the limits of the second integral and subtract it. So we're subtracting the integral from 1 to log of x. Now, 1 plays the role of a, the constant at the lower limit. At the upper limits, we don't have x. We have a function of x. And so what we're going to do is rethink our lemma in terms of some function u of x at the upper limit. But we must be careful to use the chain rule. To get the derivative with respect to x of the integral from a to u of f of t dt is f of u du dx. And now we can proceed. If we differentiate the integral from 1 to square root of x of e to the t squared dt, we get e to the square root of x squared times the derivative of square root of x. When we subtract off the second integral, that is e to the log squared of x times the derivative of log of x. This is the derivative of that complicated-looking integral. We were asked to evaluate it at x equals 1. And the rest is simply algebra. We take e to the x over 2 root x minus e to the log squared x over x. Evaluate at x equals 1, and you can check that we get 1/2 e minus 1. You will find this method useful in several problems. This is just one approach to the proof of the fundamental theorem of integral calculus. We made some restrictive assumptions in using our Taylor series understanding of what a derivative is. There are other proofs using more sophisticated means, limits perhaps, that will give you a more general result. Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 27 on improper integrals.
The fundamental theorem of integral calculus is great, but it's not without its limitations. In this lesson, we'll consider what happens when we encounter a difficulty with limits in a definite integral.
The fundamental theorem of integral calculus is great, but it does have its limitations. There are a few things that you must be careful about. In particular, the fundamental theorem has a hypothesis that f, the integrand, is continuous on the interval from a to b. And within this statement lies two dangers. The first is that of continuity. A discontinuous integrand can cause problems. Here's an example. Consider the integral as x goes from -1 to 1 of 1 over x squared dx. If we simply apply the fundamental theorem and take the antiderivative, -1 over x, and evaluate that at 1, what do we get? -1. Then we subtract what we get when we evaluate at -1. -1 minus 1 equals -2. Perfect. Except for the fact that our integrand is 1 over x squared. All those terms are positive. And if we go to the definition of the definite integral as a Riemann sum, adding up the values, there's no way that we can add up positive values to get a negative integral. The problem is this integrand is not continuous. It's not even defined at x equals 0. The second hypothesis is that of having an interval from a to b, a finite interval. Consider the integral as x goes from -infinity to +infinity of 2x over 1 plus x squared dx. Clearly, the antiderivative is log of 1 plus x squared. What happens when we evaluate this at the limits? You might think we get infinity minus infinity, which is not defined. Or you might think, well, this is an odd integrand over a symmetric domain, therefore it must be 0. Which is correct? These improper integrals are dangerous. In all cases, we're going to use the technique of taking a limit to make sense of these integrals. There are two cases. The first we might call a blow-up. This is what happens when you have an integrand that is not well defined at some point, let's say at one of the endpoints, a. In this case, the way to evaluate the limit is to integrate from some constant t to the other endpoint, and then take a limit as t goes to the singular input. In the other instance, we might call it having a tail, where your integration domain goes off to infinity. In this case, the appropriate thing to do is integrate over a finite domain, let's say up to a constant t, and then take the limit as t goes to infinity of the finite domain integral. The following class of examples are crucial to this subject. These are the p integrals, or the integral of 1 over x to the p dx. Let's consider first the example of a tail singularity, where we integrate, let's say, from x equals 1 to infinity. Of course, the value is going to depend on p, but let's do all of them at once. If we integrate x to the negative p dx, that is easy enough. That's going to equal, as long as p is not equal to 1, x to the 1 minus p over 1 minus p. We need to evaluate this at the limit x goes from 1 to t, and then take the limit as t goes to infinity. That is, we're taking the limit as t goes to infinity of t to the 1 minus p over 1 minus p minus 1 over 1 minus p. Now this limit is going to be infinite sometimes, but when p is bigger than 1, then the first term goes to 0, and we're left with 1 over p minus 1. If p is less than 1, then that first term dominates and goes to infinity, and we say the integral diverges. In the particular case where p equals 1, then this integral becomes the integral of 1 over x, that is, log of x, and evaluating that at the limits and sending t to infinity yields, again, infinity. And so we have a divergent integral when p is less than or equal to 1. Let's do it the other way and look at a blow-up instead of a tail singularity. Consider the same integrand, x to the minus p, but now integrated as x goes from 0 to 1. Well, doing the integral yields the same antiderivative. We just need to evaluate our limits differently. So, evaluating as x goes from t to 1, and taking a limit as t goes to 0. This will break up into two cases when p is not equal to 1, or when p is equal to 1. In these cases, again, we get sometimes convergence, sometimes divergence. But note what is happening to the p's. When p is bigger than 1, we get a divergent integral. When p is less than 1, then the t to the 1 minus p over 1 minus p term drops out, and we're left with an answer of 1 over 1 minus p. Again, in the case where p equals 1, log of t is not going to be convergent as t goes to 0. Let's summarize what we found with these p integrals. If we integrate along a tail going to infinity, then the p integral converges when p is strictly bigger than 1. It diverges when p is less than or equal to 1. For a blow-up singularity at 0, these are reversed, and we get a convergent integral when p is less than 1, and a divergent integral when p is bigger than or equal to 1. Note that at the particular value of 1, it's always divergent, no matter whether you're going from 0 to 1 or from 1 to infinity. Now, you don't need to remember the actual values of the convergent p integrals, but you do need to remember this chart, this listing of when the integral converges and when it diverges. And the reason you need to remember this is because it will help you determine convergence or divergence of other integrals whose antiderivatives may not be so easy to compute. Let's look at an example. Consider the integral of dx over square root of x squared plus x as x goes from 0 to 1. This is a finite domain. However, there is a singularity, or a blow-up, at x equals 0. So how should we proceed? I don't know the antiderivative to this. It doesn't look like it's going to be terribly easy. So let us consider what the leading order behavior for this integrand is. We're going to think in terms of Taylor series. Now, this integrand doesn't have a well-defined Taylor series at x equals 0, since the function is not even defined and it blows up. But notice that if we factor out a square root of x from the denominator, then we're left with 1 over square root of x plus 1 as a factor. Now let's rewrite that, thinking that we're going to be looking at what happens as x is near 0. I can write this as x to the minus 1/2 times quantity 1 plus x to the minus 1/2. And this, then, is helpful. Why? Because the binomial series says that whenever you have 1 plus x to the alpha, as x is small, then this is of the form 1 plus something in big O of x. Now, if we apply that to the 1 plus x to the minus 1/2 term, then we get the integral, as x goes from 0 to 1, of x to the minus 1/2 times quantity 1 plus something in big O of x. And we see that the leading order term in this integrand is x to the minus 1/2. So I'm going to split this up into two integrals. The first is a p integral with p equals 1/2. The second is an integral whose precise form I haven't written down, but it's something that is in big O of square root of x, and indeed is bounded, and I'm integrating it over the domain from 0 to 1. The integral on the right definitely converges. What about the integral on the left? Well, remember, I said you had to memorize some of these. Let's go back and recall that when p equals 1/2, for a blow-up p integral, it converges. Therefore, we know that this entire integral converges. We may not know the value, but we know it converges. Now, what happens if we take that same integrand and integrate as x is going to infinity? For very large x, we need to consider that x squared term in the denominator as the lead. Therefore, factoring out, we get 1 over square root of x squared times 1 over square root of 1 plus 1 over x. Simplifying that a little bit, we see that we have again something to which the binomial series applies, namely 1 plus 1 over x to the minus 1/2. Expanding that out gives 1 plus something in big O of 1 over x. And now, splitting this up into two integrals, we see that the leading order term is a p integral with p equals 1. And I don't think I need to remind you that when p equals 1, you always have divergence. Therefore, because one piece of this integral diverges, the entire integral diverges. Same integrand, different behavior as you go to infinity. There's one last thing we need to look at, and that is the problem of double limits. If you integrate something over the entire real number line, you might be tempted to evaluate the limit as t goes to infinity of the integral as x goes from negative t to t. Let's see what happens in this case. We already know that the antiderivative is log of quantity 1 plus x squared. And if we evaluate that at negative t and t, well, we get something that cancels to 0. And so it would seem as though our limit is 0. That is not correct, and we have failed to be careful. What do we need to do? We need to take two independent limits. One as, say, s is going to negative infinity, the integral from s to 0. The other as t goes to positive infinity of the integral from 0 to t. When we have two tails, we need two limits. And I don't think it's too hard to see what the behavior of each of these is going to be. If we consider what happens when x gets very large, then the leading order term is 2 over x, and what is left over is 1 over 1 plus 1 over x squared. That means that, using, say, the geometric series, we see that the leading order term is a p integral with p equals 1. That connotes divergence. And this means that each of these limiting integrals diverges, and hence the net integral does not converge to 0. It diverges. In general, you'll want to remember the p integrals and use them to tell you when an improper integral converges or diverges. These improper integrals are dangerous.
Indefinite integrals are not easy. Most students find that they have some difficulty understanding what they're supposed to do with an indefinite integral. Be sure to do a lot of practice problems in this lesson. In our next lesson, we're going to step back and take a broader look at all of the techniques that we have built. We'll apply them to a specific class of trigonometric integrals.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 27, Bonus Material. After that main lesson, you may be thinking, what is all this good for? Well, stay tuned, because when we get to Chapter 4 on applications of integrals, we're going to see that there are many instances where an improper integral tells us something about an application that we care about, whether it's geometry or probability and statistics. In fact, there are some functions whose very definitions implicate improper integrals. Let's consider the gamma function that is defined as follows. gamma of x is the integral as t goes from 0 to infinity of t to the x minus 1 times e to the negative t dt. The first thing that one has to worry about is this well defined? Does it converge? I'll leave it to you to argue that for positive values of x, we have no difficulties here. The reason being that t to the x minus 1 for any fixed value of x is going to be dominated by the e to the negative t term as the integration domain is going to infinity. Well, given that, what do people care about this function for? It is closely related to the factorial. We have stated before, implicitly, now we will state explicitly that x factorial is defined as gamma of x plus 1. Now, we hope that this is really the same thing as x times quantity x minus 1 factorial, so that this really is the factorial function, even for non-integer values of x. So let's see if we can prove that. The claim is that gamma of x plus 1 is x times gamma of x. That matches up with our intuition from factorials. So how do we proceed with a proof? Let us consider gamma at x plus 1. This is the integral as t goes from 0 to infinity of t to the x times e to the minus t dt. To handle this, let's use integration by parts. If we let u be t to the x and dv be e to the minus t dt, then du and v work out very simply. And when we apply the integration by parts formula, what are we going to get? Well, we have to take a limit as capital T goes to infinity of negative t to the x times e to the minus t, evaluated as little t goes from 0 to capital T. That's the uv term. Then we need to subtract off the next term, which is the integral, as t goes from 0 to capital T of x times t to the x minus 1 times e to the negative t dt. Now notice the minus signs conspire to give a plus sign, and notice that the limit of the first term is going to go to 0 as capital T gets very, very large. Again, that e to the minus t dominates. But when we do the other limit at little t equals 0, that too goes away. So the only thing that is left is that second term, the integral term, and taking a limit as capital T goes to infinity, what do we see? Well, we can pull out the x because it is not the integration variable, little t. And what is left is the integral as little t goes from 0 to infinity in the limit of t to the x minus 1 e to the minus t dt. That we have seen before. It is, of course, gamma of x. And so we've proven that this gamma function behaves like a factorial. Now, this is just one example of an interesting function whose very definition requires one to worry about an improper integral. We haven't discussed what happens to the gamma function when x is negative. In particular, when x is a negative integer, then you wind up having a blow up at the lower limit, at the t equals 0 case. I'll leave it to you to worry about that if you want to. If you don't worry about it. We're going to be seeing improper integrals all throughout the remainder of this course. it takes a little while to get used to the idea of not always worrying about the exact value, just worrying about convergence or divergence. But with practice and some hard work, you will get good at determining this. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 28 on trigonometric integrals.
We're nearly done with Chapter 3. At this point, we've amassed a large collection of techniques for computing definite and indefinite integrals. In this lesson, what we're going to do is collect all of those methods together and apply them to a particular class of integrals involving trigonometric integrands.
In this lesson, we'll consider 3 families of integrals involving trigonometric functions. The first, powers of sine and powers of cosine. The second, powers of tangent and powers of secant. The third, multiples of sines and cosines. Throughout, m and n are going to denote positive integers. For our first class of integrals, consider as an integrand sine to the m, cosine to the n. Solving such a problem is going to break up into several different cases, depending on whether m and n are even or odd. This will give us a good chance to practice our various integration techniques. First of all, if you're in the setting where m, the power of sine, is odd, then the following substitution will be effective. Expand sine squared as 1 minus cosine squared, and then substitute in u equals cosine. This will reduce the integral to something that is easily computed. Likewise, if n, the power of cosine, is odd, you perform a similar simplification. Expand out cosine squared as 1 minus sine squared, and then substitute u equals sine. The one remaining case is when m and n are both even. In this case, a substitution will not work. A reduction formula is required. This tends to be a bit more involved and difficult. This is the case that is going to cause us a little bit of trouble. Let's consider a specific example of the form sine to the m, cosine to the n, where m is 5 and n is 4. This puts us in the case where the power of sine is odd. Therefore, we can split off an even number of powers of sine and substitute in 1 minus cosine squared for every sine squared that we have. Now you see that there is 1 power of sine left over, so that if we perform the substitution where u equals cosine theta, we have a copy of du minus sine theta d theta sitting in the integrand. And we wind up getting minus the integral of quantity 1 minus u squared squared times u to the 4th du. This polynomial can be expanded out and then easily integrated. Substituting back in u equals cosine theta gives us a solution. Negative cosine to the 5th over 5 plus 2 cosine to the 7th over 7 minus cosine to the 9th over 9 plus a constant. Likewise, if we had an odd power of cosine, then we could apply the same method where we substitute in 1 minus sine squared for cosine squared, and we have left over a single power of cosine. Another u substitution will easily solve this integral. Integrals involving powers of tangent and secant follow a similar pattern, depending on the parity of the powers. If one is in the setting where the power of tangent is odd, then perform the simplification, expanding out every tangent squared as secant squared minus 1. Then substitute in u equals secant. Likewise, if n, the power of secant, is even, then one can simplify every secant squared as 1 plus tangent squared. The substitution u equals tangent will then work. The one remaining case where a reduction formula is required is when n, the power of secant, is odd, and m, the power of tangent, is even. Let's consider a specific example, in this case where the power of tangent is 5 and the power of secant is 6. Then, because the power of secant is even, one way to solve this integral is to split off a secant squared and replace the remaining even powers of secant with quantity 1 plus tangent squared. This means that when we do the substitution u equals tangent, we have a copy of du sitting right there to be absorbed. This yields a polynomial integral of the form u to the 5th times quantity 1 plus u squared squared. By expanding that out, integrating that polynomial, and substituting back in tangent for u, we easily obtain the answer: tangent to the 6th over 6 plus tangent to the 8th over 4 plus tangent to the 10th over 10 plus a constant. However, there's another way to solve this integral as well, exploiting the fact that m, the power of tangent, is odd. In this case, what we'll want to do is split off an even power of tangent. Substitute in secant squared minus 1 for tangent squared, and then use the fact that there is a secant tangent left over to perform a substitution where u equals secant theta. There remains in each class that we've considered one case where a simple substitution does not work. This requires a reduction formula. The first step is to simplify to sums of powers of cosine or secant. For example, if we look at the integral of sine to the 4th cosine to the 4th, this is in that one case where both powers are even. We can replace sine squared with 1 minus cosine squared and obtain a sum of integrals, each of which is an even power of cosine. Then we can apply integration by parts twice to obtain the following general reduction formula. The integral of cosine to the n is cosine to the n minus 1 times sine over n plus n minus 1 over n times the integral of cosine to the n minus 2. This simplifies or reduces the level of complexity of the integral involved. Likewise, for powers of secant, one can express the integral of secant to the n as tangent secant to the n minus 2 over n minus 1 plus n minus 2 over n minus 1 times the integral of secant to the n minus 2. Now, you do not have to memorize these formulae. They're the type of thing that one looks up when you're stuck on a difficult integral. Let's apply this reduction formula in the specific case of the integral of cosine to the n. Recalling the reduction formula for powers of cosine, we're going to have to apply this iteratively many times until we get down to a low enough power of cosine that we can proceed. To make things a bit more concrete, let's do a definite integral as theta goes from negative pi over 2 to pi over 2. When we do so, one of the things that's nice is that the term cosine to the n minus 1 sine over n in the reduction formula vanishes when we perform the evaluation. And so, for n greater than 1, we get that the definite integral from negative pi over 2 to pi over 2 of cosine to the n is n minus 1 over n times the same integral with the power being n minus 2. This will allow us to come up with a recursive solution. So let's look at all the different powers. In the simplest case, where n equals 0, well, we can do that integral. The integral of d theta is theta evaluated from negative pi over 2 to pi over 2 gives pi. Likewise, we can do n equals 1 explicitly, integrating cosine, getting sine, evaluating at the limits gives us the value of 2. Now, for higher powers, we can use the reduction formula. All we have to do is multiply by n minus 1 over n. So to get n equals 2, we multiply 2 minus 1 over 2, that is 1/2, times the integral in the case where n equals 0. To get the value for n equals 3, we multiply the value for n equals 1 by 3 minus 1 over 3. We can continue for increasing values of n, always looking back to n minus 2 and multiplying by n minus 1 over n. Now let's look at this. What do you notice? Well, first of all, it seems as though there's a real dependence on whether n is even or odd. When n is even, there's a factor of pi involved. And when n is odd, there's not. That's maybe not so surprising, seeing that even and odd powers have been different all throughout this lesson. In general, using a little bit of induction, one can show that when n is even, the result of this integral is pi times 1 over 2 times 3 over 4 times 5 over 6, etc., all the way down to n minus 1 over n. When n is odd, one obtains a similar looking result, but starting with 2 instead of pi, and flipping things. The result is 2/3 times 4/5 times 6/7, all the way up to n minus 1 over n. All of that times 2. By putting a 1 down in the denominator, we can see a familiar pattern between these two definite integrals. Now there's one last class of integrals that we're going to look at. That is, something of the form, the integral of sine of m theta times cosine of n theta. The sine wave and the cosine wave have potentially different periods. Now, this integral requires an algebraic simplification. The following formula is something that you do not have to know or have memorized, but which is extremely useful. That is, sine of m theta times cosine of n theta equals 1/2 sine of m plus n theta plus sine of m minus n theta, at least in the case where m and n are not the same. If we integrate both sides with respect to theta, then we obtain the formula negative cosine m plus n theta over 2 times quantity m plus n minus cosine of m minus n theta over twice quantity m minus n. And you can see here why m and n have to be different. Likewise, one can do the same thing for sine of m theta times sine of n theta. A similar reduction gives an integral that is computable. Likewise, with a pair of cosines of different periods, the result works out. Once again, these are not the kind of formulae that you memorize, but they are useful to look up. Now, why would any of these integrals be useful to us? One important reason is that sines and cosines, trigonometric functions, pervade the physical universe. If you go far enough in mathematics, you will learn about Fourier analysis, which is a mathematics built on sines and cosines. It's extremely useful in analyzing any kind of wave, whether acoustic or electromagnetic. In fact, one could argue that all of radar and signal processing is built on a basis of integrals, sines and cosines. Now you know a bit about how to compute them.
I think you'll agree. Some of those integrals were kind of tricky. What do you do when faced with harder and harder integration problems? Do you have to employ ever more clever tricks? No. Mathematics is not about tricks, but rather about principles. However, when having to solve a difficult problem, we have to use every available method. In our next lesson, we'll give a brief introduction to those methods that are computer-assisted.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 29 on Tables and Software.
In this course, I've de-emphasized graphing calculators and other computational tools for solving calculus problems. However, when it comes to integration, there's only so much that I can teach you in this course. Many integral problems are simply too difficult to be solved by hand, and computers provide a wonderful tool. In this lesson, we'll give a brief introduction to some of the software-based tools available and cover what they can and cannot do.
Not all mathematics computations can or should be done with pencil and paper. I inherited from my father several old slide rules, which are wonderful analog devices for doing mathematics. I can remember my first calculator, simple though it was, soon to be replaced by more capable devices. But there are older technologies still, one of which is books. In particular, when doing a difficult integral, one might find it useful to go to an integral table. These typically appeared in the back of the big, thick calculus textbook. Let's see an example of how these tables might be used. Compute the integral of 3 dx over x minus 4 plus 4 over x. What one would typically do is go to the back of the book and scan up and down the table to look for some formula that matched the form of what you were trying to solve. Now, this might work, it might not. If it doesn't, well, one would typically try to do some algebraic simplification. Let's say, in this case, multiplying through numerator and denominator by x. In that case, then factoring the denominator gives something of the form x over x minus 2 quantity squared. Now that is something that does appear in our integral table. One has the integral of x over quantity ax plus b quantity squared, and the formula follows from that. Now, I'm sure that you could figure out how to do this with partial fractions, but let's use the table. In this case, what would one have? Well, b is negative 2, and a is equal to 1. And so, following the formula, one gets negative 2 over x minus 2 plus log of x minus 2 plus a constant. Oh, wait, we have to multiply everything by that 3 that was out in front. And that's how one would use a table. Fortunately, there are better methods available now with the advent of cheap and fast computation. There are several software packages that are available for doing mathematics, integrals in particular being something a bit more challenging than derivatives. We're going to focus on one of these called Wolfram Alpha. If you go to wolframalpha.com, then you'll see a screen come up that allows you to type in whatever you're interested in exploring. You'll have to play around a little bit with some of the mathematics notation involved, but it shouldn't be too unfamiliar. Let's do a simple example, in this case e to the x. And in this case, after a few moments of thinking, it will give us a bit of information. For example, it will give the graph of the function over various ranges. It will also tell us something about roots. Well, in this case, there's not much there. The domain, the range. It will notably give Taylor expansions, and it will do so using big O. So it's a good thing that we've learned that already. It will tell about derivatives and integrals and other information as well, including limits and various series expansions. Let's try a challenging integral and see what we get. We'll try to integrate sine cubed of x over 2 times cosine cubed of x over 2. After thinking for a moment, let's see what it comes up with. Well, it gives us an answer, 1 over 96 times quantity cosine 3x minus 9 cosine x. It even remembered the constant. That's wonderful. It will also give us graphs associated with this answer, other forms of the integral. Very important in this case, since the way that I would have done the problem might have led to a different looking answer. It will give series expansions, again using big O language. Now, in what I'm showing you here, Wolfram Alpha allows you to click the Show Steps button. Unfortunately, they've changed that functionality, and it's no longer available for free. You can, however, pay for a service which allows you to expand out all of the intermediary steps in how to arrive at this answer. As you can imagine, that's something that could be pretty useful. Well, let's consider a different example. Let's see how hard we can make it and see what Wolfram Alpha will be able to do. Let's consider the integral of 1 minus x to the 7th, third root, minus 1 minus x cubed, 7th root. And let's make this a definite integral, x going from 0 to 1. And let's see what happens in this case. Well, it's giving us an answer, and that answer happens to be 0. But why? Well, Wolfram Alpha doesn't tell you why. But if you consider these two pieces, the 7th root of 1 minus x cubed and the cube root of 1 minus x to the 7th, with a little bit of thinking, you'll see that these two pieces are inverses of one another. If you compose one into the other, then you'll get the identity back. And that means that the graphs of these functions are symmetric about the line y equals x. And since we're going from 0 to 1, where it intersects the x-axis, that means that the integral of the difference between these two must be 0, because anything on the left is balanced out by the corresponding piece on the right. Wolfram Alpha does a great job, but it doesn't explain the why. Let's say that we wanted to solve that same integral, but instead of making it a definite integral, we tried to type it in as an indefinite integral, figuring perhaps we'll evaluate the limits and come up with the answer on our own. Well, in this case, the indefinite integral is not so simple. It's expressed in terms of hypergeometric functions of two variables. Well, this is not a wrong answer, but it's not exactly illuminating for where we're at right now. So, like any tool, you have to use it with caution and with intelligence. Let's consider a different example. This one, again, a difficult definite integral. The integral of sine to the n over a quantity sine to the n plus cosine to the n. Notice that we didn't have to specify what our variable was, in this case x. It intuits that we mean sine of x to the nth power, etc. Let's evaluate this as x goes from 0 to pi over 2. Well, after a little bit of thought and a little bit of more thought, we get a properly interpreted question, but an answer that says, no, not happening. Now, this is a free product, so we don't expect it to have supercomputer-like abilities. But let's try to work with what we have. I claim that one can show that the answer to this definite integral is pi over 4. This involves some tricky trigonometric formulae. I'm not going to show it to you, but let's say you suspect that this definite integral has a nice answer. What could you do? Well, let's try typing in something for a specific power, for a specific n. In this case, n equals 3. Then Wolfram Alpha is able to handle that one very nicely. It gets not only the correct decimal answer, but the exact answer of this integral. Very good. Now let's continue with a higher power still. In this case, n equals 5. Well, at this point, Wolfram Alpha still gets the correct numerical answer, but it no longer knows that that is really pi over 4. And if we move to higher powers still, well, things are going to break down. But whatever difficulties might arise, this and other computational tools are extremely useful. With a little bit of practice and some thinking, you can use this and other computational methods to solve problems. But more than that, you can use these tools as a means of exploring mathematics. In fact, you may discover new results or theorems. Computation has always pointed the way to new truths and new ideas, and there is so much left to be done in mathematics. With these tools in hand, you, too, might make a contribution. I encourage you to play with these tools.
You've reached the end of Chapter 3, but this is by no means the end of our reliance on integrals. Indeed, in Chapter 4, we will turn to applications of indefinite and definite integrals and see some classical and some modern ways in which these are used.